Right. Please confirm me, all of you. Can you see here board and other things? Right. Just give me 1 minute. I'll come back 1 minute. Right. So I'm back. Right. So we'll continue our discussion. What is that means? So once again, please confirm me, all of you. Raise the hands if you can hear me, please. Right. So I think in the last class I have drawn the equivalent circuit of a three-phase induction motor, the complete equivalent circuit. Let me draw that once again. So the complete equivalent circuit I'll draw once again. Right. This is R2. This is JX2, R1, JX1, RC, JXM. So these are the effective turns of stator, and these are the effective turns of rotor, and this is V1 per phase. So here you can see the difference between the turns ratio and the number of turns and effective turns. So what does that means? If N1 represent the actual turns, actual stator turns, N2 represent actual rotor turns, then you know that in case of the stator winding, the windings are distributed and they are being short pitch. What is the reason to distribute and short pitch? You know the reason, right? So NES, I call it as the effective turns of the stator, which is N1 into KW1. So what is that KW1? The winding factor. And NER is N2 into KW2. So what is that N2? the actual rotor turns, and Kw2 is the distribution that is winding factor of your rotor winding, right, or rotor side. So here K is defined as NER by NES, that is equal to 1 by A, right? I hope this is clear. So please remember, in case of transformers, if you want to define the transformation ratio K, it is defined as the ratio of secondary turns to primary turns. But here it is effective turns of rotor to the effective turns of stator. So effective turns is nothing but actual turns into the winding factor, right? I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. So here only few what happens to others. Please all of you attend, raise the hands. Right. So if I want to calculate the performance parameters, I need I2. But because you know already, if you know the value of I2, then you can calculate the rotor input power, then you can calculate the rotor losses, then you can calculate the rotor output power, then you can calculate the torque developed by that motor at that particular slip. And if the mechanical losses are all given, then you can calculate the net power also. Already we have seen how to calculate all those things when we have only the rotor circuit parameters, right? But here I'm having both stator circuit as well as rotor circuit parameters. Then if I want to calculate this I2 for this circuit, it is very difficult. Why? Because due to the presence of that so-called as the transformer. So in order to reduce the difficulty in calculating I2, what I'll try to do means I'll try to refer all the rotor circuit parameters to stator side. So when I'm trying to refer all the rotor circuit parameters to stator side, I can eliminate the need of transformer, right? So the presence of transformer I can eliminate, right? This point was already discussed in the last class. Please confirm me, all of you. Confirm me, all of you. Right. So here, if I want to refer the rotor side parameters to stator side, first of all, the same frequency parameter should be changed. So what is the meaning of same frequency? If I'm calling E2 as the EMF induced in the rotor winding during running condition, then what is the equation for I2 here? I2 is equal to E2 by R2 plus J X2, X2. So this is equal to S E2 naught by R2 plus J S X2 naught. So from this you can see the frequency component in this is SF, and the frequency component in this is SF. So it is not possible to refer that X2, which is a variable whose frequency is SF, from rotor side to stator side. Similarly, E2 I cannot refer. Similarly, I cannot refer I2. Why? Because the frequencies of those currents, EMF and the reactance is SF. I cannot refer. So if I want to refer how to modify the circuit, already you know how to modify the circuit. For this, what I'll do means I'll divide with S and I'll divide with S. If I do that, I2 is equal to E2 naught by R2 by S X2 naught. So what is the frequency component in this F? What is the frequency component in this F? What is the frequency component in this F? R2 by S is a resistance. So resistance is independent of frequency. If I modify the circuit like this, then I can refer the rotor circuit parameter to stator side. But the thing is, even if I represent the running parameters with standstill parameters, there is no change in I2. I can refer, I can rewrite. Is this point clear? Confirm me. Confirm me. Right. So I'm replacing this circuit. I'm replacing this circuit with that new circuit. Right? So how to replace that means I'm not drawing the right hand side, I'm replacing. So this is E2 naught This is R2 by S. This is J X2 naught. This is I2. I2. The remaining part I'm not drawing. It is understood, right? So first thing is I made the rotor circuit frequency to be same as the stator circuit frequency. This point is over. So all this is to refer your rotor circuit parameters to stator side to calculate the value of I2 now. I2 now, right? Done. The second thing is, I think in your transformers, you might have learned that. If not, you are going to learn when you are referring any resistance from one side to another side, the ohmic losses should not be changed. So whatever the ohmic losses we are having with R2, when it is in the rotor side, even if it is referred to the stator side, the ohmic losses should remain same. Similarly, X2 naught, which is accountable for the reactive power drawn from the source, leakages is accountable for the reactive power. So whatever the reactive power the machine draws with X2 naught on the rotor side, even if it is referred to the stator side, the reactive power drawn should be same. So like that we need to find out, right? I think this is clear. So for that, what I'll try to do means just I pre-assume that you know, otherwise you'll learn, don't worry. So when R2 is coming from rotor side to stator side, it becomes R2 dash. Then where R2 dash is equal to R2 by K square. Similarly, when X2 naught is coming to stator side, let me call it as X2 naught dash, but I write it as X2 dash. This is my intention. So your imagination, you can write anything, X2 naught by K square. Similarly, when E2 naught is coming to the stator side, it will become E2 dash, and this E2 dash is equal to, let us call E2 naught by K. Similarly, when I2 is becoming to stator side, so it becomes I2 dash, it is K into I2. K into I2. So what is that K here? K here is effective turns of rotor by effective turns of stator. I hope this is clear. So here you can see these two values are given and you can calculate K and you can calculate these values. Is this point clear? Is this point clear? Right. Now I'm referring. So I'm referring. If I refer that, the circuit will be like this. This is R2 dash by S. This is JX2 dash, right? So when that voltage is referred to this side, this becomes E2 dash. This current becomes I2 dash. So this is R1, JX1. This is RC, JXM. I hope it is clear. Confirm me, all of you. Confirm me, all of you. All right. So here, if the question is like this, calculate the performance of an induction motor. If they ask how to calculate the performance of an induction motor means, see, I'll be explaining the procedure. See, I can calculate efficiency. How to calculate efficiency? It is a ratio of P net by PSI into 100. How to calculate P net? P net is equal to 3 I2 dash square into R2 dash into 1 by S minus 1 minus the mechanical losses. So if I want to calculate P net, what is required for us? I2 dash is required. And if I want to calculate PSI, then I need 3 V1 per phase I1 cos theta. So I need to find out this. Just 1 second, some disturbance. right? So you can calculate. So if you want to calculate the performance of the machine, so the only thing is you should know I2 dash. If you know I2 dash, then you can calculate the rotor input power. You can calculate the rotor losses. You can calculate the gross mechanical power. If in addition to these equivalent circuit parameters, if the mechanical losses are given separately to you, then even you can calculate the net power and also can calculate the torque of that motor, the torque developed by the motor, right? So the only thing is I need to calculate E2 dash, sorry, I2 dash. If I once again I'll repeat, if I know I2 dash, I can calculate the rotor input power, the rotor losses, the rotor output power. If mechanical losses is provided separately, if they are provided separately, I can find out the net mechanical power. Then I can calculate the rotor side parameters. Then if I want to calculate the efficiency of that motor, then I need to know the input side. So here V1 is given. So if I want to calculate efficiency, what is required to me is I1. So if I want to calculate I1, then I have to apply the network reduction technique, or I can go for, so if you know this I2, then you can calculate the voltage here. Once you know the voltage here, you can find out I1 as this voltage minus this voltage by the impedance. You'll get the value of that I1. So once you are having I1, you can find out the performance, that is efficiency of the motor. Is this point clear? Is this point clear? Is this point clear? Right. Now the question is, still modify the circuit here. Still I can modify the circuit here. How means? In this, I will eliminate this RC. What is that RC? RC I can eliminate me. So this RC is not dependent on your currents. This RC depends upon your supply voltage. Why? Because it is accountable for the core losses in the stator. And you know that these core losses are all constant losses. So for that, what I want to do means, still in order to reduce the complexity in calculating that I2 dash, in the analysis, I'll neglect that RC. So I cannot directly neglect that RC. But here, when I'm neglecting that RC, the stator core losses has to be given separately to you. See? So some people are raising the hands. From my side, it is clear. All of you confirm me. From my side, it is clear. Right. See, Baba, one or two has raised the hands. It may be from your side the technical issue. Please try to rectify that. I'm neglecting RC. So still to reduce the complicity, RC is not considered in the analysis. But however, while calculating the net power, in addition to mechanical losses, core losses should be subtracted from the gross mechanical power. See one thing, tomorrow in your examination, if RC is given, just listen, please try to understand. If RC is given, if you want to calculate the net mechanical power, which information alone is sufficient means the mechanical losses. But in the equivalent circuit parameters, if RC is not given, then it means that the core loss branch is neglected, but in the analysis it is neglected. but whatever the factor that is accountable, it is separately given. So in that case, how to calculate P net means, so P net in that case will be 3 I2 dash square into R2 dash into 1 by S minus 1 minus mechanical losses plus core losses. Core losses. So when we are neglecting that RC in the analysis, that means that core losses has to be given separately. Then you have to add in that mechanical losses when you are calculating that net power. I think this point is clear. Confirm me. Confirm me. Right. Then how the circuit will be reduced now? How the circuit will be reduced now? So this is R1, this is JX1, this is JXM, this is R2 dash by S, this is JX2 dash, and this is I2 dash. So this is V1 per phase. I think this point is clear. Confirm. See, all this groundwork we are trying to do to calculate the value of I2 dash. Once again, I'll repeat. See, so when I was explaining about the rotor circuit parameter, the rotor equivalent circuit, so if you want to calculate the performance parameters like full load or whatever it may be, so if you want to calculate this, then first of all, you should know the value of I2. Then how to calculate I2? We have seen once you are having I2, then you can calculate the rotor input, rotor losses, rotor output. Then you can calculate the torque at that slip. Even from the rotor equivalent circuit, you can calculate the full load torque, maximum torque, starting torque, like that. Everything we can find out if you know the rotor circuit parameters and also the value of S. Is this point clear? Is this point clear? Right. So here also what I'm trying to do means I'm trying to represent the motor completely. When I'm representing the motor completely, in addition to that rotor circuit, we have drawn the stator circuit also. Just like your approximate analysis, if I want to calculate the rotor circuit parameters, then definitely I should know the value of I2. So if I know the value of I2, then for that circuit, it becomes a difficult thing. Why? Because due to the presence of the transformer. So in order to reduce the complexity, I need to refer all the rotor circuit parameters to stator side. If I want to represent the rotor circuit parameters to stator side, the frequency should be same. I made the frequencies to be same, right? Then after that, when I'm referring the parameters from one side to another side, when you are referring your resistance, the ohmic losses should remain same. Just I'll try to give that. What is that? I2 square into R2 should be equal to I2 dash square into R2 dash. So from this, R2 dash is equal to I2 by I2 dash whole square into R2. So your I2 dash is nothing but your I1. If I neglect your no load current, then it is nothing but 1 by K. So like that, we got the value of R2 dash. Similarly, you can calculate the other parameters, right? Now we are done with that referring the rotor circuit parameter to stator side. So in this, if you are having the value of I2 dash, then you can calculate the rotor circuit parameters, rotor input, rotor losses, rotor output. In addition to that, if the mechanical losses are given separately with R1, R2 and other things, then you can calculate the net power also. How to calculate the net power? Like this. But RC represent your core losses, and core losses depends upon voltage, and voltage is a fixed parameter. For that, I am relieving that RC from the analysis. But when I'm relieving that RC from the analysis, what is that RC accountable? It is accountable for core losses. So that is the reason in this particular case, when the RC value is not given, if you want to calculate the net power, then you have to subtract in addition with mechanical losses, the core losses to get the net power, like this. So tomorrow in your examination, while the equivalent circuit parameters are given R1, R2 dash, X1, X2 dash, Xm, and if RC is not given, then you have to clearly see, in addition to that, mechanical losses, core losses are not given or not. If they are not given, it is not possible, RC should be given. For example, if RC is also given, but while you are calculating the net power, only mechanical losses has to be subtracted or they has to be deducted. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. Now, this is a simple electric circuit now. Now, if I want to calculate the unknowns, what are those unknowns? I1 and I2 dash. Why? Because I1 is required to calculate the input side, and I2 dash is required to calculate the rotor side. Then I can go for a simple network reduction technique. Simple network reduction technique. What is that? So these two are connected in parallel. Then for this parallel, this branch is coming in series. Then you calculate a Z equivalent here. Then I1 is equal to V by Z equivalent. Then I2 dash, either by using current division rule or by using another method, you can calculate I2 dash. Once you are having I1 and I2 dash, you can completely find out the performance of that machine. Is this point clear? Is this point clear? Is this point clear? Right. So like this, we can calculate the values of I1 and I2. But what is the main difficulty for this means? For example, say, I'll take one example. See. I'm having an induction motor. The value of R1 is equal to say 0.15 ohms. The value of R2 dash is equal to say 0.12 ohms. The value of X1 is equal to X2 dash is equal to 0.45 ohms, and Xm is equal to say 28.5 ohms. You want to calculate the motor efficiency when the slip is 4%. Slip is 4%. Say you want to calculate. So if you want to calculate the motor efficiency, then what is required for you? The net power is required and the input power is required. And in addition to that, the constant losses are given. Constant losses means it is given sum of mechanical losses plus core losses are given to you. Say something like 400 watts. So this is the data given. So first, what is that you need to do means, first for a given slip, you need to calculate R2 dash by S. It is 0.12 by 0.04. It is something like 3 ohms. Then you substitute that 3 ohms here, then J0.45 here. Then you calculate this parallel impedance. After that, you calculate the series impedance, the Z equivalent. From that, you calculate the value of I1. From that, you calculate the value of I2. Once you are having I1 along with theta 1, you can calculate the input power and you can calculate the net power and you can calculate the efficiency. Is this point clear? Is this point clear? But what is the main difficulty we are having with this means? Main difficulty we are having with this means, whenever the value of S is changed, whenever the value of S is changed, then you need to start the procedure from the beginning. What do you mean by from the beginning? See, when the value of S is changed from say 0.04 to 0.03, then if you want to calculate the current and again the powers and other things, from where you need to start from 0.12 by 0.03, it is 4. So from that, these two are connected in series, like that. You need to calculate the parallel impedance, Z equivalent, I1, I2 dash, like that. You have to start the procedure from the beginning. I hope this point is clear. Confirm me, all of you. Right. So to rule out this difficulty, so we are not finding out that I2 dash, So using this network reduction technique, we are calculating this I2 dash using your Thevenin's theorem approach. So once I'm having I2 dash, then I can calculate all the performance parameters, even I can calculate the torque also, right? So let us see how to calculate that I2 dash. So here, here I2 dash is calculated using Thevenin's theorem. Thevenin's theorem. Once again, I'll go back. Why? Because you should know what I am doing, right? Without that something, if I do calculations, it is a meaningless procedure, meaningless task. See, we are having a complete equivalent circuit of an induction motor. When I'm talking about the complete equivalent circuit, R1 will be given, R2 will be given, X1, X2, RC, XM, V1, NES, NER, all these things are given. Then say if you are asked to calculate the motor efficiency at a particular slip, then you need to know the value of I2 and you need to know the value of I1. But for that complete exact equivalent circuit, it is not possible to calculate I2 dash. Why? Because there is a presence of transformer. So to rule out that problem, what I have done is I have referred all the rotor circuit parameter to stator side. So when I'm referring the rotor circuit parameter to stator side, first I made the frequencies same. Then I have considered that ohmic losses should be same. Like that, we have referred all the rotor circuit parameter to stator side. After that, we are having RC. What is that RC represent? The core loss branch. So that core loss branch is not going to be affected much, even if it is there, if it is neglected in the analysis. Why? Because it is dependent on your voltage, but not on current. So to make this calculation still easier, simpler, I'm simply ignoring that RC. But when I'm ignoring that RC, it is not like just you ignore. But whenever you are ignoring that RC, you are not considering the core losses. So that core losses has to be given separate along with that mechanical losses. If they are given separately, I can ignore that. I can proceed with the calculation. So I'm ignoring here. I'm proceeding with the calculation, right? See, some people are raising the hands. I think from my side, I don't have any issue. Please raise the hands once. Right, no problem, sir. Fine. So I think it is clear. See, Baba, those some 4 or 5 students are raised from my side. No issue. Please try to rectify your side. Thevenin's theorem, right? So how to find out that I2 dash? I pre-assume that you know Thevenin's theorem. What is that first step in Thevenin's theorem? First step in Thevenin's theorem, remove the branch, remove the branch, remove the branch, R2 dash by S plus J, X2 dash, and assign the terminals as AB with voltage across AB as VThevenin. VThevenin, right? I'll do that. See, A, B, VThevenin. R1, JX1, JXM. This is V1 per phase. Up to here, confirm me, all of you raise the hands. Sibaba, I'm not teaching circuits, but you know the steps. What is the step? If you are applying a Thevenin's theorem, first you need to remove the effect of that branch from the circuit. So your steps are, so if you want to calculate the current in a particular branch using Thevenin's theorem, then what you need to do means first you need to remove that branch and you need to assign the voltage across those terminals as AB. I have done this, right? I think this point is clear. After that, calculate VTH and calculate ZTH. Step 2. Step 2. Calculate VTH and ZTH. ZTH is equal to RTH plus J XTH. right? So I need to calculate VTH and ZTH, right? See, if I want to calculate VTH, then I'll be applying the voltage division rule. I can go for anything, voltage division rule. So I'll be calling this impedance as Z1 and this impedance as Z2, right? So VTH is nothing but the voltage across that impedance or that branch Z2. So what is that voltage division rule? The voltage across any branch is equal to the total voltage into the same branch impedance by sum of the impedances, right? Once again, if I want to calculate VTH, I can go for anything. What is that? I can calculate the current in this loop. So that current into that impedance will give that voltage. That is one way, but I'm going a simplest way. That is voltage division rule. So the voltage across AB is nothing but the voltage across Z2. So if I want to calculate the voltage across Z2, then I'll be making use of voltage division rule. What is that voltage division rule? The voltage across any impedance or any branch is equal to total voltage into the same impedance by some impedances. I think this point is clear. Confirm me all of you. Confirm me all of you. Raise the hands. Right. So if that is the case, so VTH is equal to what is the total voltage V1 per phase. Please remember, I told you all the times. I told you all the times. The line voltage is joker. We don't need the line voltage in any of your calculations. We need only the phase voltages. Why? Because we are using impedances. So impedances are always designed for or explained for phase. Please remember that. Into JXM by the total impedance. What is the total impedance? R1 plus J X1 plus XM. X1 plus XM. Is this clear? So this voltage is equal to this impedance by the sum of the impedance. Please confirm me all of you. Confirm me all of you. Right, done. But here I can still modify. So these are all valid for your exam engineering service. Please see. If you look into these numerical values, so these are some practical values. Practical values. Then in this, what is the value of R1? You can see R1 is equal to 0.15. What is the value of X1? 0.45. What is the value of XM? It is 28.5. You can see here. So R1 is equal to 0.15 and X1 plus XM is equal to 28.95. Why? Because 28.5 plus how much it is? 0.45. So it's 28.95. You can see when compared to X1 plus XM, so this R1 value is very, very, very less. Very, very less. So please remember, when compared to X1 plus XM, the value of R1 is less. Is this point clear? Is this point clear? Confirm me. All right. So VTH is equal to mod V1 into J XM by J into X1 plus XM. So here JJ gets cancelled, right? Then I call this ratio XM by X1 plus XM. For a given motor, this ratio will remain constant, and I name that constant as alpha, some alpha. So different textbooks may use different constants. I take some alpha. So VTH is equal to how much now? It is mod V1 into alpha. So mod V1 into alpha. So this is the Thevenin's voltage, where V1 is the per phase voltage. Per phase voltage. Per phase voltage. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So first let me proceed. After that I'll come. Don't worry. Then after that I need to calculate ZTH. So how to calculate ZTH means it is the impedance in across the open circuit terminals. See one thing, when I'm talking about equivalent circuit analysis, means it is something about your circuit analysis. So whatever you might have learned in your node analysis, mesh analysis, something like steps, I'm doing the same thing. Just only this will have some calculations. The remaining thing will be having mostly theory, right? Please. So when I'm calculating that Z Thevenin's, the active sources should be killed. That means they should be represented with your internal impedance. So here this has to be represented with a short. Why? Because this is a voltage source, this has to be represented with a short. I think this point is clear. Confirm me, all of you. Confirm me, all of you. Right. If I represent that, how the circuit will be like this? The circuit will be like this. It is R1 JX1 XM A B. Right. This is Z1. This is Z2. Correct. Now, if you see this AB, you need to calculate the impedance across AB. If you see this, one end of Z1 is connected to A, the other end of Z1 via the short circuit it is connected to B. That means Z1 is connected between A and B. I think this point is clear. Confirm me. Confirm me. Right. Then if I take this impedance Z2, one end is connected to A, the other end is connected to B. That even Z2 is also connected between A and B. So these two are connected in parallel now. These two are connected in parallel now. Then what is the Z Thevenin's now? So these two are connected in parallel means, so Z Thevenin's is equal to R Thevenin's plus JX Thevenin's, that is equal to JXM into R1 plus JX1 by R1 plus JX1 plus XM. Again, when compared to this X1 plus XM, this R1 can be neglected. Then if that is the case, JXM into R1 plus JX1 by JX1 plus XM. Then if I simplify this, then I'll get R1 into alpha plus JX1 into alpha. Alpha is the same XM by X1 plus XM. So I'll take one numerical, you can understand that, don't worry. So from that, what is the value of R Thevenin's? You got R Thevenin's is equal to R1 into alpha and X Thevenin's is equal to X1 into alpha. Like that we calculate the values of RTH and XTH. Is it clear? Confirm me. Is it clear? Confirm me. Right. Only few. What happens to others? Please raise the hands. It is only the theory, network theory I'm doing, please. Then step 3 is draw the Thevenin's equivalent circuit. Just hold. Draw Thevenin's equivalent circuit. Thevenin's equivalent circuit. So what is the Thevenin's equivalent circuit we are having? So it is VTH, RTH, JXTH. This is the Thevenin's equivalent circuit, right? Then connect the branch which is removed in step 1. What is the branch that is removed in step 1? It is R2 dash by S plus J X2 dash. And this is your I2 dash. Then how to calculate I2 dash here? So I2 dash is equal to V Thevenin's by square root of R Thevenin's plus R2 dash by S whole square plus X Thevenin's plus X2 dash whole square, right? So like this, you can calculate I2 dash. Once you are having I2 dash, you can calculate rotor input power, rotor losses, the gross mechanical power developed. As mechanical losses and core losses are combinedly given, you can calculate net power. So rotor circuit is over. Then if you want to calculate the stator side, then once you are having I2 dash, then how to calculate I1? You are having I2 dash, you have calculated I2 dash. So I2 dash into this impedance will give E2 dash. this impedance will give E2 dash. Why? Because I2 dash into R2 dash plus JX2 dash, that will give E2 dash. Once you are having E2 dash here, then this is V1. So V1 minus E2 dash will give the so-called as I1. Once you are having I1, you can calculate the input side parameters also. Is this point clear? Confirm me. Confirm me, all of you. Right. Then what is the advantage we are having with Thevenin's theorem over network reduction technique? The thing is, so if you want to calculate I2 dash using this so-called as network reduction technique, what is the procedure? First, you need to calculate R2 dash, then that branch impedance, parallel impedance, Z equivalent, I1, I2 dash. Like that, you have to calculate. But once that slip is changed, again, you have to follow the same procedure. But here, there is no need to follow the same procedure. So once the slip is changed, so here only this parameter is variable. Why? Because for a given motor, this is constant, this is constant, this is constant, this is constant, this is constant. Then what is the only variable here? Yes, you can use that yes there. You can calculate I2 dash. Again, you can calculate I1. You can calculate everything. So which procedure is simpler means the Thevenin theorem approach is very, very simpler. Very, very simple. I think this point is clear. Confirm. Right. So once again, I'm repeating. Once again, I'm repeating. So just let me see. Right, forgot to write today. Today is which day? Day 12, I think. Let me write here. Right. So I don't know. So just I'll go back. Right. See. Yeah, I'm here. See. So if only rotor circuit parameters are there, if I know the value of I1, sorry, if I know the value of I2, if I know the value of I2, what are the things you can calculate? Rotor input, rotor losses, rotor output, the electromagnetic torque we can find out, right? So the only thing is I should know the value of I2. But here for the circuit that I2 becomes difficult. So for that what I have done is I have referred all the rotor circuit parameter to stator side and I have calculated I2 dash. Once I know the value of I2 dash, I can calculate rotor input, rotor output, rotor losses, everything I can find out. So how we have calculated that I2 dash means we have not used a network reduction technique, but we have used the Thevenin's theorem approach. Why we have used the Thevenin's theorem approach means when compared to your network reduction technique, for every value of I need to follow the procedure. So whenever that slip changes, I need to calculate R2 dash by S. Like that, I have to follow the procedure. But Thevenin's theorem approach will not tell that. So whenever the slip changes, you can calculate the value of I2 dash directly. I2 dash directly. I think this point is clear. Confirm me. Confirm me. Right. Then how to calculate the torque? How to calculate the torque? So what is the equation for torque we are having? Electromagnetic torque is 180 by 2 pi ns. It is I2 square into R2 by S. So this I2 square into R2 by S, this I can write it as I2 dash square into R2 dash. Why? Because the values are being referred to the stator side. So what is the equation I'll get for the torque here? Electromagnetic torque is equal to 180 by 2 pi ns I2 dash square into R2 dash by S. So I'll substitute that I2 here. This I2 I'll substitute here. 180 by 2 pi ns with evidence by square root of R Thevenin's plus R2 dash by S whole square plus X Thevenin's plus X2 dash whole square into R2 dash by S. Then if I simplify this, I'll get one torque equation. What is that? 180 by 2 pi ns v Thevenin square by r Thevenin plus r2 dash by s whole square into r2 dash by s. This is the equation for torque for any value of slip ranging from 0 to 1. So this torque we call it as exact torque equation. Exact torque equation. Exact torque equation. I hope this is clear. See, the procedure for that approximate steady state analysis and the procedure for exact steady state analysis is same. That means if I want to calculate the rotor circuit parameters, I should know the value of I2. So what is that we have seen in I2, how we have calculated that I2 in case of approximate we have seen. But here in case of your complete exact equivalent circuit, it is not possible to calculate I2 directly. So for that we have referred that I2, that rotor circuit parameter to stator side. Then from that using Thevenin's theorem approach, we have calculated I2 dash. The same thing I2 dash can be found using your network reduction technique also, but there the procedure will be complicated. Why? Because for every value of slip you need to start from R2 dash by S, but whereas in case of Thevenin's theorem approach there is no need to go for calculating R2 dash by S every time. Then we have to calculate VTH, RTH, XTH. From that we can calculate I2 dash whenever there is a change in slip without a regular procedure. I think this is clear. Confirm me all of you. Confirm me all of you. Right. Right. So tomorrow, for example, the question is asked. If the question is asked, see, you can just see I'm having a three-phase induction motor. Okay. The equivalent circuit parameters of these three-phase induction motors are this. These are the equivalent circuit parameters. The motor is excited with 400 volts, 50 hertz supply. Can you calculate the value of S? So then, can you calculate the value of current, rotor current, when it is operating at a slip of 0.04? Yes. So if I want to calculate that, first I need to calculate VTH, RTH, XTH. If I want to calculate VTH, I need alpha. According to our definition, alpha means XM by X1 plus XM. Once you are having alpha, you can calculate VTH, RTH, and XTH. Then after that, you can calculate I2 dash when the slip is 4%. Is this point clear? Confirm. Confirm. Anyhow, I'll take one example you can understand. Now, can you please calculate the same current? Can you please calculate the current when the slip is 3%? Yes. Then there is no need to calculate VTH, RTH, XTH. Why? Because for that motor, with that excitation, I know the values of VTH, RTH, and XTH. So if I want to calculate the current at 3% slip, just remove that 0.04, place 0.03, then you can get the value of the current at 3% slip without again calculating all these things. Is this point clear? Raise the hands. Now, can you please calculate the current at 2% slip? Yes. So there is no need to calculate VTH, RTH, XTH. Why? Because we know for that motor all those values. Then take S is equal to 0.0 to calculate that I2 dash. But if you are using this network reduction technique, so if you want to calculate that I2 dash for 4% slip, first you need to calculate R2 dash by S for 4% slip, then parallel impedance Z equivalent I1, I2 dash. If you want to calculate the current at 3% slip, then you have to calculate R2 dash by 0.03, then the procedure has to be followed. So every time you have to follow the procedure. So to rule out that problem, we are using which theorem? Thevenin's theorem approach to calculate that I2 dash. I hope this is clear. Finally, confirm me once, all of you. Confirm me once. Right. Then I need to calculate the other performance parameters. What are those? So we are done with the rotor circuit parameters. I want to calculate full load torque, maximum torque, and other things, which we already done using rotor circuit. First performance parameter is full load torque. Get ready with the calculators. You need to give the answer. Full load torque. full load torque. What is that full load torque? Full load torque is nothing but electromagnetic torque when slip is the full load slip. Again, I'm not giving the definitions. You know the definitions. So what is the equation for full load torque? It is 180 by 2 pi ns V Thevenin's by V Thevenin's or V Thevenin square here. Good. V Thevenin square R Thevenin's plus R2 by S FL whole square plus X Thevenin's plus X2 dash whole square into R2 dash by SFL. This is the equation for which torque full load torque. So you know what is the definition for full load torque means? It is one value of torque when the windings are carrying the rated current when the supply voltage is rated in the range 0 to 1. I hope this point is clear. So let us solve one numerical, then you can understand all these things, right? This is a common data. A three-phase 400 volts 50 hertz 4-pole star connected induction motor has the following per phase equivalent circuit parameters in ohms referred to stator side. So R1 is equal to 0.15. It is not per unit. Why? Because it is already given in ohms. R2 dash is equal to 0.12. X1 is equal to X2 dash is equal to 0.45 and Xm is equal to 28.5. These are the equivalent circuit parameters. Calculate the full load torque if the full load slip is 4%. Do it. I'll give 2 minutes time. Right. So here I can. So the only thing is alpha. What is that alpha? Xm by. See, this alpha has not taken any patent that always the ratio should be x1 plus xm. In our case, that is like this. Right? Do it. I'll give 1 minute time. Just do it. I'll just call you back. Come you. 277 Newton meter. Very good, Sham. See, anonymous attendee, how to remember a big equation, sir? See, Baba, this is not a big equation. Simple thing. See, there is no logic, there is no magic here. So you have to be, should follow this. Just wait. Right. There is no logic in this. See, how to remember means no need to remember. You remember this Thevenin's equivalent circuit. If you remember this Thevenin's equivalent circuit, then calculating this I2 dash is not a big difficulty. Once you are having I2 dash, substituting in this torque equation is not a big difficulty. Then you can calculate the torque. So if anyone is having any difficulty in remembering this equation, the best procedure is the full load torque is equal to 180 by 2 pi ns I2 dash FL square into R2 dash by SFL. Why? Because the slips at full load I am replacing. Then how to calculate I2 dash FL? That is V Thevenin's by square root of R Thevenin's plus R2 dash by SFL whole square plus X Thevenin's plus X2 dash whole square. Once you are having this current, you can calculate torque. That is the easiest way. If you feel if it is difficulty, but I don't suggest you to go with this second step. Why? Because it is something like trouble in remembering all the time. Better you remember this. I think this point is clear. Confirm me, all of you. Confirm me, all of you. Right. I'll go one by one. Please try to answer me. I'll go one by one. So please help me with the answers. So here given VL is how much? 400 volts. I told you that unless and until specified, the given voltage is always a line voltage. But in all our calculations, we need which voltage? Phase voltage, right? And you can see here, the windings are connected in star. Then what is the per phase voltage? V1 per phase is equal to 400 by root 3. So that is 230.9 volts. Is it clear? Confirm me, all of you. Is it clear? Right. Done. Then I need to calculate alpha. Alpha is equal to how much? Xm by x1 plus xm. So what is the value of xm? It is 28.5 by 0.45 plus 28.5. So can anyone give me the answer for xm? I'm waiting. Xm 0.984. Tell up to 3 digits. 0.984. Done. Then what is the value of VTH? VTH is equal to mod V1 into alpha. That is 230.9 into 0.984. How much it is? 227.4. What is the value? 227.4. Yes. 4 volts. Then what is the value of RTH? RTH is equal to R1 into alpha 0.15 into 0.984. So it is 0.147 ohms, if I'm correct. Please tell me. RTH is how much? 0.147, right. Similarly, what is the value of XTH? It is X1 into alpha 0.45 into 0.984, that is 0.443. I think this is clear, right? Done. Then what is the value of full load slip given? In this case, full load slip is 4%, that is 0.04. Then how to calculate full load torque? Full load torque is 180 by how many pole machine it is? 4 pole. What is the synchronous speed for 4 pole and 50 hertz? It is 1500 into 227.4 square by R Thevenin's 0.147 plus R2 dash 0.12 by 0.04 square plus X Thevenin's 0.443 plus 0.45 square whole square into 0.12 by 0.04. If you simplify this, it is 276 point something. I can make it as 277 Newton meters. So this is the full load torque. See, generally in GATE, such a lengthy question may not be asked, but still I'm trying to explain the procedures, right? So this is the exact value. So on what basis I'm calling this one as the exact value means we have considered both the stator side values and the rotor side values, right? I hope this is clear. Confirm, all of you. Raise the hands. Right, done. So this is the first performance parameter. The next performance parameter which I need to calculate is the maximum torque. I'm not defining the definitions again. Why? Because already you know maximum torque. Maximum torque. So if I want to calculate maximum torque, first of all, I should know the value of slip at maximum torque. Sir, already we are having R2 by X2 not now. We cannot use here. Why? Because that is applicable only for the so-called as rotor circuit parameters. Now here you have to follow the same. Mean procedure is same, but the slip value will be different. Let me see how it is. Some people have texted. Okay. In denominator whole square is not there. Very good. Thank you. Done. Maximum torque. How to calculate maximum torque? Right. Next one is calculating the slip at maximum torque. Maximum torque. That is S MT and the value of maximum torque, right? So if I want to calculate that, what I need to do, I have to take the torque equation again. What is the torque equation we are having? And I have to differentiate this equation with respect to S, and I should equate to 0. Then I can need to calculate the slip at maximum torque, right? But very unfortunately, so it is very difficult to follow this procedure. So to rule out this procedure, I'll be making use of maximum power transfer theorem, right? So again, I'll write the same thing here. To obtain the ST max, use either optimization techniques or maximum power transfer theorem. Maximum power transfer theorem. See, why I'm not telling all these things means you know already, right? Just I'm giving the outlines. Optimization techniques are maximum power transfer theorem. Using for optimization techniques, differentiate equation 1 with respect to S equal to 0. 0. I hope this is clear. Confirm me. Confirm me. So in maximum power transfer theorem, what is that we need to do? Maximum power transfer theorem, what we need to do? So if you recall your torque equation, what is the torque equation? 180 by 2 pi ns I2 dash square into R2 dash by S. So if I want to have this torque to be maximum, then this rotor input should be maximum, right? If this has to be maximum, then R2 dash by S should consume maximum power, right? So for that, I need to modify the equivalent circuit. How to modify? You take this rotor equivalent, that is a Thevenin's equivalent circuit. This is a Thevenin's equivalent circuit. So which branch I need to show it as a load now means which branch I have to show here? R2 dash by S. Why? Because the torque is dependent on that. See, I'm not doing any new concepts. Whatever we have learned in the approximate, I'm doing the same thing. And I'm trying to shift this branch here. Then according to maximum power transfer theorem, this impedance should be equal to this impedance, right? So it is R dash by S should be equal to square root of R Thevenin square plus J square. Any doubt or any disturbance, right? Optimization techniques. I have not done any optimization techniques here, right? So optimization techniques means you have to differentiate that equation with respect to S and you have to equate it to 0. See, for maximum torque, so I'm trying to do that. So from this I can calculate SMT. See, one student was eagerly asking, sir, such questions will be asked in engineering service examination. See, with respect to your prelims, 100% they will not ask such questions. But with respect to mains, definitely they will ask. And in gate, it is true that he may not ask the full load torque, but he may ask what is the slip for maximum torque. So that is the reason I'm covering each and every topic. Please remember, Baba, you please don't read on the basis of your exam. Please try to read on the basis of subject. You should know all the topics. Please remember. So from this, what is the value of ST max R2 dash by R Thevenin square plus X Thevenin x2 dash whole square under root. This is the slip corresponding to which one? Maximum torque. Once again, I'm repeating. Say I'm having a 3-phase induction motor, and for the 3-phase induction motor, the equivalent circuit parameters are given to you. What are those equivalent circuit parameters? R1. Now here R2 dash referred values are given. R2 dash X1, X2 dash XM, all are given to you. Then it is something like this. Assume that this machine is in New Delhi and you are in Hyderabad. The question to you, Are Baba, whatever the motor you have designed, which is in New Delhi, can you please tell me what is the maximum torque value of that motor? Then to be honest enough, if I want to find out that, what I need to do means I need to go to New Delhi and I need to conduct a suitable load test till I need to add the load, the motor is about to stop, then I need to calculate the torque, and I can say the maximum value of or maximum torque value of this motor is this much. So that is by conducting a suitable load test, we can find out the maximum torque of that motor. But here, without the physical load test, even the motor is not available with us, the motor is in New Delhi and we are in Hyderabad, then from the equivalent circuit parameters of that motor, I can find out the maximum torque of that motor. So if I want to calculate the maximum torque of that motor, first of all, I should know what is the slip at which the torque will be maximum. So if I want to calculate the slip at which the torque is maximum, then I can use either optimization techniques or I can use that maximum power transfer theorem approach. So if I want to go for that optimization techniques, then you take the torque equation and you differentiate the torque equation with respect to S and you get it to 0. So from that you get the value of slip at which the torque will be maximum. But that will be a lengthy and something laborious work. Why? Because U by V you have to go. The other way to calculate the same slip is using that maximum power transfer theorem. So what is that maximum power transfer theorem says? That means if the load impedance is made equal to the source impedance, then that so-called as load will consume maximum power. So here if you look into the basic torque equation, so this torque equation says that if R2 dash by S is consuming maximum power, then the rotor input will be maximum. When the rotor input is maximum, then the torque developed by that motor will be maximum. So for that, what I did is I took this Thevenin's equivalent circuit, I modified the circuit in such a way that R2 dash by S I kept like a load and that X2 dash I shifted to that source. Then I have applied that maximum power transfer theorem. So from that we got the slip at which the torque will be maximum. So what is the slip at which the torque will be maximum is it is R2 dash by square root of R Thevenin's square plus X Thevenin's plus X2 dash whole square. Using this we can calculate the slip value at which the torque will be maximum. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Now you may have a by default question. Such questions will be asked in gate. 100% such questions will be asked in gate. Please remember such questions. That means the equivalent circuit parameters will be given to you, and that is stator side as well as the rotor side. And you may be asked to find out what is the slip corresponding to maximum torque, and you may be asked to find out what is the slip at that, what is the speed at that maximum torque. Please remember that. Right. Done. So how to calculate the speed? So this is the slip at maximum torque. So please tell me 6:44. I'll give 2 minutes break. I have to break the fast, right? So you tell me 6:44. Just raise all of you raise the hands. So this is the slip at maximum torque. Not now 6:44 I told maximum torque. Then how to calculate the speed? How to calculate the speed? The speed at maximum torque is equal to ns into 1 minus st max. Like this you can calculate. Up to here clear? Up to here clear? Raise the hands. Right. Then how to calculate maximum torque? See, one thing, let me remind you. So tomorrow, no student should feel that sir has not explained this way, this procedure. And I'm trying to explain all the steps and at the same time, what are the possible questions, right? Please remember that, right? Done. Then how to calculate maximum torque? So maximum torque is nothing but the electromagnetic torque value when that R2 dash by S is equal to square root of R Thevenin's square plus X Thevenin's plus X2 dash whole square. So I'll substitute this condition in this torque equation. Which torque equation? In this torque equation, right? If I substitute, what I'll get? Say I'll substitute, then I'll give the answer directly. So electromagnetic torque is nothing but maximum torque. It is 180 by 2 pi ns V Thevenin square by, so it is R Thevenin's plus, in place of R2 dash by S, what is that I need to substitute? It is square root of R Thevenin square plus X Thevenin plus X2 dash whole square plus X Thevenin plus X2 dash whole square into, again you are having R2 dash by S. So again in place of that R2 dash by S, you have to write square root of R Thevenin square plus X Thevenin plus X2 dash whole square. X2 dash whole square. Just give me 2 minutes time and tell you the easiest way also. So if you simplify this, some 5, 6, 1, 2, 3, 4, 5, 6, some 7, 8, 9, 10 steps, then finally I'll be having this maximum torque value like this. So T max is equal to 180 by 2 pi ns 0.5 V Thevenin's square by R Thevenin's plus square root of R Thevenin square plus X Thevenin plus X2 dash whole square. So this is the equation for your maximum torque value. Then by general, why? Because you people are like the modern age students, you need the shortcuts for all the things. Sir, is it possible or is it necessary to remember this equation? Generally no. Then how to calculate maximum torque, sir? The simple procedure is, tomorrow if the question is asked for a given three-phase induction motor equivalent circuit parameters, calculate the maximum torque of that motor. Then first what you need to do means you need to calculate this slip for sure. First you need to calculate that slip for sure. Once you are having that slip, you substitute that slip in this current equation. In this current equation, which you already did. This current equation. You will get the I2 dash at maximum torque. Once you are having current, then 180 by 2 pi ns, 180 by 2 pi ns, that current square into R2 dash by ST max will give the maximum torque value. Right. See, now I'm back. Right. So if the question is asked, calculate the maximum torque, means first you need to calculate the slip. You substitute that slip value in the current equation, that is V Thevenin by square root of R Thevenin plus R2 dash by that slip whole square plus X Thevenin plus X2 dash whole square. Once you are having that current, then maximum torque is equal to 180 by 2 pi ns I2 dash that current square into R2 dash by ST max. We'll get the value of maximum torque. Is this point clear? Is this point clear? Is this point clear? Right. So if you have a full memory, then you can remember this maximum torque equation. Why? Because nowadays, what I observed from my experience is the question is asked like this. If R1 is R1, R2 dash X1, X2 dash XM are the equivalent circuit parameters, then what will be the equation for the maximum torque developed by a three-phase induction motor? That question is asked directly. In that case, definitely have to remember this equation. What is that equation? 180 by 2 pi ns 0.5 V Thevenin square by R Thevenin plus square root of R Thevenin square plus X Thevenin plus X2 dash whole square. So it is up to you. So there are two ways to calculate this maximum torque. What are those two ways? I'll tell. Way one is calculate slip at maximum torque using the formula R2 dash by square root of R Thevenin plus X Thevenin plus X2 dash whole square. After that, calculate this current at maximum torque. After that, you calculate maximum torque is equal to 180 by 2 pi ns I2 dash the current at maximum torque square into R2 dash by ST max. This is one way. The other way is, if the question is asked to calculate the maximum torque directly, so T max is equal to 180 by 2 pi ns 0.5 V Thevenin square by R Thevenin plus square root of R Thevenin square plus X Thevenin plus X2 dash whole square. This is the second way, right? See, Baba, just bear for some 10-15 minutes. So calculation part will be over with this, right? Please. Only in the equivalent circuit, you find some lengthy equations. You find most of the calculations. Why? Because it is equivalent circuit analysis. Circuit analysis. So if I'm talking about in networks, you find less theory, more numericals. So here also equivalent circuit analysis. So that induction motor is represented in electrical circuit form, and using that electrical circuit form, you are calculating all the performance parameters. So that is the reason it is something like circuit analysis, circuit calculation. So there is no chance, there is no way to skip this, to avoid this. I hope this is clear. Confirm me all of you. Confirm me all of you. Right. Then violate for the above problem, this problem, common data problem. This problem, this common data. For the above problem, for the above problem, calculate slip at maximum torque, the rotor speed at maximum torque, and the value of maximum torque, right? So I'll keep the equations here, right? Please try to calculate. First you calculate the slip, then after that you can calculate the torque. First you calculate the slip and tell. First calculate the slip and tell. See, Baba, I told how you got 0.5, sir. That's what I told you, anonymous attendee. So here, if you simplify 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, then you'll got 0.5, right? You try to check that, right? You can derive if you require, but it is not required as of now. That's the reason. Anonymous attendee, is it clear? So there are some 7 to 8 steps. Please go for that step, you'll get it. Right, what is the answer for ST max? I'll give the equations. It is R2 dash by square root of R Thevenin square plus X Thevenin plus X2 dash whole square. Then what is the rotor speed at maximum torque? Then what is the equation for maximum torque? Right, please tell me. Please tell me what is the value of ST max. ST max is 0.1326. Okay. 0.1326. It is only the substitution. Speed 0.1326 is correct. What is the speed? Speed 1301 RPM. Right, very good. Then what is the value of maximum torque? maximum torque value. Are 1499? How come, Baba? No. 1500 into 1 minus 0.1326. Right, Vikrant? Please try to cross check. Speed is okay. Then torque 468, roughly 470 you will get. No problem. The torque is 468 point something you got 86. So I can make it as 469. So Newton meter. So if you take some other decimals, you'll get 470 also, right? 470 also. X2 value, how sir? Where is that X2 value? It is given in the numerical. Please remember X2 dash, not X2, right? Please refer that. So this is something about which torque? The maximum torque, right? Done. Yes, you can replace yes with maximum torque, someone, right? Right. So I'll repeat once again, please. Please, please see all of you. Listen, I'm updating myself. Please. If anyone questions you, Arey, I have an induction motor and this induction motor is in New Delhi and I want to calculate the full load torque of that three-phase induction motor. If you want to calculate the full load torque of that induction motor, then what you need to do generally, go to New Delhi, give the rated voltage at rated frequency to the motor and try to operate the motor with the rated speed by applying some mechanical brake drum arrangement. Then take down that input power using that wattmeters, measure that output mechanical power, then do calculations and calculate the full load torque. That is the general way. But instead of that, so without going to New Delhi, from Hyderabad itself, I can find out the full load torque. Conditions apply. If the person who is staying in New Delhi provides you the equivalent circuit parameters and along with the full load slip. If the equivalent circuit parameters and the full load slip is given to you, then you can calculate the full load torque without going to New Delhi. This is what we have done in the first case. I think this is clear. Confirm me, all of you. Confirm me. Right. In the second case, I need to calculate the maximum torque of that motor. If I want to calculate the maximum torque of that motor, first I need to find out the slip at maximum torque. Then we have a formula for this. After that, I need to calculate the current. Then from that, we can calculate the maximum torque. Otherwise, we have a formula directly to calculate the maximum torque. And using that formula, we can calculate the maximum torque. I hope this is clear. Confirm me, all of you. Confirm me, all of you. Raise the hands. Raise the hands, all of you. Right. Oh, 6:44. Thank you. So I'll just take 2 minutes. It is not break, right? 2 minutes. I'll come, not just I'll break, then I'll come back. 2 minutes. Right. So I'm back. Thank you for your support. Right. Right. So thank you. Right. I hope you understood how to calculate maximum torque. Is it clear? Confirm me, all of you. Right. So what is the only difference between the full load torque approach and the maximum torque approach? Means in full load, the slip at full load will be given. Then for that you need to calculate the torque. But whereas in case of maximum torque, that slip will not be given. You need to calculate the slip and you need to calculate the torque. The next one is starting torque. Starting torque. You can see the procedures what we have followed for approximate steady state analysis, and this is same. So starting torque is nothing but electromagnetic torque value when S is equal to 1. So I'll take the torque equation, which equation? This equation. In place of S, what is that I need to substitute here? In place of S means I have to substitute 1. Then I'll get the starting torque. It is 180 by 2 pi ns V Thevenin square by R Thevenin plus R2 dash by 1 whole square plus X Thevenin plus X2 dash whole square into R2 dash by again 1. 1. If I simplify this, T start is equal to 180 by 2 pi ns V Thevenin square by R Thevenin plus R2 dash square plus X Thevenin plus X2 dash square into R2 dash. So this is the equation for which torque? The starting torque, right? See, the only thing is I have taken that exact torque equation. In that S value we are varying, then accordingly we are finding out all these things, right? Is it clear? Confirm me. Confirm me. Right. Then while for the above problem, the common data. Above problem, calculate starting torque. Starting torque. Calculate this. Calculate this. Give the answer. Vikrant. Very good, Baba. 136. What is this answer? So one has given the answer, at least many. Only one student has given, Vikrant. (136) Imtiaz Pasha, right, Baba. So it is 136 Newton meter. We can just substitute 180 by ns is for the above problem it is 1500. Then you can substitute all the values. Then you will get the starting torque, right? Done. So it is something like this. Array, the motor is in New Delhi. I am giving the equivalent circuit parameters of that motor. Can you please tell me what is the full load torque value of that motor? Then I'll question him back. I'll provide the answer for full load torque, but you tell me what is the full load slip. Then that person will go to the nameplate details who is in New Delhi. You'll check what is the full load slip value. And if you provide the full load slip, then you can calculate the full load torque of that motor from Hyderabad itself. The second one is I need to calculate the maximum torque. So for that, I don't need anything. So we have a derivation and we have a equation to calculate the maximum torque. And from that, I can tell the maximum torque of that motor. The next one is I can calculate, sir, change the location, sir, change the location, sir, how many times that New Delhi? Okay. So this time we'll go for some, you tell anonymous attendee, which place you want to tell, some place you want to tell, okay? Okay. Then if I want to calculate Goa, okay, you want to go to Goa, what a good selection, Singapore, wow, so Singapore, Dehradun, Mumbai, leave it, fine. Then I want to calculate the starting torque. So without attending the machine physically from the equivalent circuit, I can calculate the starting torque. I think this is clear. Confirm me all of you. Confirm me all of you. Right. So one student said that Kodada. Right. Anyhow. So this is something about your the three performance parameters. I'm updating myself to you. See. So we are calculating the exact steady state analysis. What is the meaning of exact steady state analysis means? Without having a physical motor, without conducting any physical load test, we can completely determine the performance parameters of that three-phase induction motor. So if I want to completely determine the performance parameters of the three-phase induction motor, the three-phase induction motor has to be represented electrically. We have represented the three-phase induction motor electrically. And if I want to calculate performance parameter, I need to know the value of I2. But from there, you know, if I want to calculate the value of I2, as you can see a transformer in between the primary and secondary circuit, so it is very much difficult. So to reduce the complexity in calculating that I2, we have referred all the parameters to rotor side, to stator side. When I'm referring that parameters from rotor side to stator side, we have seen the frequencies are made same. Then that when R2 is coming to this side, how it changes, like that we have seen. Finally, we brought the complete circuit referred to stator side. But still in that I can still modify that. I can remove that RC and I can go for the equivalent circuit. Then we have removed that RC, but that core losses because of that RC are accounted in calculating that net power separately. Then if I want to calculate that I2 dash, we are having two approaches. One is that network reduction technique. But using that network reduction technique, if you want to calculate that I2 dash for every value of slip, you need to start the procedure from R2 dash. So to rule out that, we have calculated or we have represented that I2 dash using your Thevenin's theorem. So once we are having I2 dash, I can completely find out the performance of that motor. Once I'm having I2 dash, I can find out each and everything. Why? Because that current will change with the slip. When current changes, the torque will change. The powers will change, right? So if you want to calculate the rotor side parameters at a slip of 3%, then first you calculate I2 using that S is equal to 0.03, then calculate input, rotor output, rotor losses, torques, we can find out. After that, we have calculated the full load torque of that motor, maximum torque of that motor, starting torque of that motor, right? I hope this is clear. Confirm me all of you. Confirm me all of you. Right. The next performance is if I want to obtain maximum torque at starting, what resistance I need to add in the rotor circuit. Next performance parameter is finding out. I remind you one thing, today our regular class, the doubt session will be after 9. The regular class will be up to 9. I think I told you in the previous class. Remember that. Calculating the value of external resistance required in the rotor circuit to obtain maximum torque at starting. maximum torque at starting. See, what was the procedure we have done in case of approximate? We took St max is equal to R2 plus R external by X2 naught. Then we have to get this maximum torque at starting. From that, we calculate the value of R external is equal to X2 naught minus R2. This is using rotor circuit parameters. I hope this is clear. Confirm me, all of you. So here also I need to follow the same procedure. But here it is not possible to calculate R external directly. Why? Because all the values of the rotor circuit are referred to stator side. First I calculate R external dash. Once I'm having R external dash, then I can calculate R external, right? Let us see. So let St max, that is slipper's maximum torque, is equal to R2 dash plus R external by square root of R Thevenin square plus X Thevenin square plus X2 dash whole square. This should occur at starting. Then from that, what is the value of R external dash? R external dash is equal to square root of R Thevenin square plus X Thevenin plus X2 dash whole square minus R2 dash. Once you are having R external dash, then how to calculate R external? So R external is equal to K square into R external dash. R external is equal to 1 by A square into R external dash, where K is the transformation ratio secondary to primary and A is the turns ratio primary to secondary, right? So like this, you can calculate the additional resistance required in the rotor circuit to obtain maximum torque at starting. Then violate for the above problem, the common data. For the above problem, calculate R external for obtaining maximum torque at starting. Take A, that is stator to rotor turns ratio as 1.2. Do it. First calculate. First you tell what is the value of R external dash. After that you calculate RE. Please do it. First you calculate R external dash. Tell that value. Then after that you can calculate R external. 0.78. Very excellent. 0.785. This is 0.785 ohms. Then you tell what is the value of R external. Right. 0.553. 0.553. So this is something about your so-called as yes, not 53, 544, 0.545. 0.545. Yes, done. So this is the fourth performance parameter. Then what is the last one? Maximum internal mechanical power. Last one is maximum internal mechanical power. See, once again, I'm reminding you, this is equivalent circuit analysis. When I'm talking about equivalent circuit analysis, this means involving more circuit analysis part, right? Please remember that, right? Can we keep this RE in the equivalent circuit? Yeah, you can keep to obtain maximum torque at starting. That should be in the rotor side. But the equivalent circuit which you have designed is in stator side. In that case, you have to put RE dash. Sai Charan Reddy. Please remember that. Is there any problem from my network connection? You are clear with me? All of you raise the hands. Yes. Fine. Done. Right. Next one is calculating the slip at maximum internal mechanical power. Maximum internal mechanical power and maximum internal mechanical power. Maximum internal mechanical power. Maximum internal mechanical power. So what is the formula we are having? Pi max is equal to 3 I2 dash mm square. See one thing, after this, you'll be having an interesting topic, that is starting methods. You don't have so many calculations there, but it is very important. R2 dash into 1 by SMM minus 1. So if I want to calculate this, I need these two. Then how to calculate I2 dash mm? I2 dash mm is V Thevenin by square root of R Thevenin plus R2 dash by SMM square plus X Thevenin plus X2 dash whole square. So if I want to calculate this, I require this. So how to calculate that means SMM is again using maximum power transfer theorem. See, all these approaches we have discussed when we are talking about rotor circuit parameters, same procedures, right? Here, SMM can be calculated using maximum power transfer theorem. Now you please tell me, this is dependent on which resistance here? This is dependent on this resistance, R2 dash into 1 by SMM minus 1. Then I have to modify the circuit in such a way that which branch we need to show it as a load now, R2 dash into 1 by R2 dash into 1 by SMM minus 1. Now let me take the rotor circuit. First let me take the complete circuit. I'm splitting this into two parts. What are those? R2 dash into 1 by S minus 1. So which one I have to keep it as a load here? I have to keep this one as a load. Then I'll throw this here and I'll throw this here. If I do that, minus 1. So I'll be equating this impedance to the source impedance. Square root of So from that you calculate the slip. Right. So first you are having slip, after that calculate current, after that calculate power. Like that you can calculate the maximum internal mechanical power of that motor. Then while it, for the above problem, calculate internal mechanical power maximum. Do it, all of you, do this. Do this. Slip is 0.104. Excellent. What is that heading, sir? You can see the heading is maximum calculating. This is the heading. Calculating the slip at maximum internal mechanical power and the maximum internal mechanical power. Right, please. Right. See, I didn't took ST max is equal to 1. See, Vijay, Rani, Reddy. See, if I add how much resistance in this circuit so that this maximum torque will occur at starting. So actually ST max is equal to what is the formula, R2 dash by something. If I add some resistance in the rotor circuit, this slip will be varying. I need to know how much resistance I need to add in the rotor circuit. I need to add how much resistance in the rotor circuit to obtain that maximum torque at starting, right? Vijay Rani Reddy, I hope you are clear. Right. So very good. Finally, someone gave the answer. Slip is 0.104. Someone gave the answer finally. So the maximum internal mechanical power is, how much it is? 65 kilowatts. You can do this. 65 kilowatts. You can do this. You can do this. So like this, we can completely find out the performance parameters of your induction motor. So finally, let me summarize. You can do that. I'm leaving to you as a homework. Let me summarize. If anyone questions you, are without a physical motor, a physical induction motor, is it possible to find out the complete performance of a three-phase induction motor? Yes. How? Means I'm going to divide that complete performance into two parts. One is the approximate steady state analysis, the exact steady state analysis. In approximate steady state analysis, only you know the rotor circuit parameters, and using the rotor circuit parameters, you can find out the complete performance of that induction motor. But as you are considering only the rotor circuit parameters, so whatever the values you get will be only the approximate values. But the same performance parameters can be calculated if both stator side as well as the rotor side parameters are given. That is called as exact steady state analysis. So in all the things, what is we need means I2, the rotor current. If you know the rotor current, then I can find out the performance of that motor easily. But for a complete exact equivalent circuit, due to the transformer presence, it is not possible to calculate that I2. So to calculate that I2, what we have done is we have referred all the rotor circuit parameter to stator side, and the remaining procedures or the remaining things are simple. I hope it is clear. Confirm me all of you. Confirm me all of you. Right. Then after that, we'll go for approximate equivalent circuit. What is this approximate equivalent circuit? Means I'll tell you one thing. After this, I'll give break. Right? I'll introduce. Right? 1 second. 1 second. After this, I'll give break. right? What is this approximate equivalent circuit? Means see, please listen. See, if I consider the exact equivalent circuit referred to stator, exact equivalent circuit referred to stator, if I have equivalent circuit referred to stator, what is the exact equivalent circuit referred to stator we are having? This is the exact equivalent circuit referred to stator. R1 JX1 XM R2 dash by S J X2. This is P1 per phase. Even this circuit, we call it as IEEE recommended circuit. So this is the exact equivalent circuit of an induction motor referred to stator side. So here all the values are given. V1, R1, X1, XM, R2 dash, X2 dash, everything is given. And if you want to calculate the performance parameter, then you need to know the value of I2 dash. If I know I2 dash, I can tell everything with respect to that motor. If I want to calculate I2 dash, we have seen two ways. One is network reduction technique. The other one is Thevenin's theorem approach. So using these two things, we can calculate your I2 dash. But what is the difficulty we are having in network reduction technique means the procedure has to be started from R2 dash by S for every value of slip. Say you are calculating that I2 dash for a slip of 4%. Then you need to find out R2 dash by S. Like that, you have to calculate I2 dash. If you want to calculate that I2 dash for another slip 2%, then you have to start from R2 dash by S only. So it is a laborious way, it is a lengthy way to calculate your I2 dash. Then further, there is a shortcut, that is Thevenin's theorem. So I have represented that I2 dash in terms of Thevenin's voltage, Thevenin's resistance, and Thevenin's reactance. Then if you want to calculate S, you have to substitute only that S, you can calculate current. If S is varied, other parameters will be constant. You substitute that new S, you calculate the current. Like that, we can calculate that I2 dash. So the easiest way to calculate this I2 dash is Thevenin's theorem approach. Is it clear? Confirm. Confirm. Yes. Why we are having such a difficulty in calculating this I2 dash means this stupid fellow JX. This stupid fellow JXM. If that JXM is not there, then if this fellow is not there, then this I2 dash is equal to the voltage by the total impedance. I can find out. Or even if this JXM is shifted across the source, I can calculate your I2 dash without any difficulty. Now let us see. Is there any difficulty we are having in shifting that branch JXM across the source? When I'm shifting that JXM across the source, we should not have any difficulty, right? So what is that approximate equivalent circuit means? We are trying to shift the JXM branch across the source and finding out the performances. But even after shifting that JXM across the source, we may not have that much difficulty in calculating, we may not have that much change of I2 dash calculating after stator impedance before stator impedance. Once again, why? So you can see this is the stator impedance R1 plus JX1. This is after. This branch is after. If this branch is shifted before, then we may not have difficulty in calculating I2 dash. What is that? Let me just draw. You can understand like this. R1 JX1 R2 dash by S JX2 dash. Then in this case, this I2 dash is equal to V1 by square root of R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square. So this we call it as approximate equivalent circuit. So you can see this is a shunt branch or magnetization branch. In exact equivalent circuit, it is after the stator impedance, But whereas in case of approximate equivalent circuit, this is before the stator impedance. But even if you are changing the branch from this side to this side, there should not be much change in the performance parameters. Only in that case, I can go for shifting. Now we are going to see, even if this branch is shifted before to the stator impedance, there will not be much change in the values. So for that, we proceed with approximate equivalent circuit only, right? The next concept is approximate equivalent circuit. We'll see that then after some 15-20 minutes, this concept will be over. Then we are going to see what are the questions previously asked in GATE engineering service from this. After that, we can talk about the starting method, which is a very, very important concept. This year, you can expect a question from starting method, definitely, right? We'll see, right? What is the difference between previous calculation of internal power and this? Dupati Bhavani. In the previous calculation, we have not considered the stator circuit parameters, but in this, we have considered the stator circuit parameters also, right? Anonymous certainly give the break. Yes, I'm giving the break, right? We'll meet after the break. Right. So all of you confirm me. Can you hear me? Raise your hands. All right. So I'll proceed. Approximate equivalent circuit. Approximate equivalent circuit. Refer to stator side. Stator side. This is the heading. So here we have the exact equivalent circuit referred to stator side is given by already you know what is that. X2 dash, right? So this is the exact equivalent circuit referred to stator side. So here, if I want to calculate this I2 dash, we have difficulty, we have the complicity. Why? Because of that shunt branch JXM. So if you want to calculate this I2 dash, so we are having two ways. One is the network reduction technique. The other one is the Thevenin's theorem approach. So why we are having such a difficulty in calculating that I2 dash is this so-called as the shunt branch elements JXM, right? Now, if I'm trying to shift this branch from here to here across the source, now that complexity can be reduced, the difficulty can be ruled out. But when I'm trying to refer that branch from across the source, across the load, or after the series impedance to before to the source, there should not be change in the performance parameters, right? See, if I consider this Z1, this Z1, what is the current that is flowing through Z1? I1. So here I1 is equal to I0 plus I2 dash. So the drop in Z1 is due to I0 and I2 dash. I2 dash, right? The current which is flowing through Z1 is I1, which is nothing but the phasor sum of I0 and I2 dash. But here, this I0 value will be very less compared to I2 dash, and hence the drop in Z1 due to that I0 will be much lesser compared to the drop in Z1 due to this I2 dash. So as the magnitude of that no load current is less compared to that I2 dash, then the drop in that Z1 due to that I0 will be very less, and hence we can ignore that. We can ignore that or neglect that. If I'm neglecting, then I can shift this branch from here to here. So I'll do that. If I do that, it will be like this. R1 Jx1 R2 dash by S Jx2 dash. This is V1 per phase I0. So what is the voltage we have across this V1? So in this case, what is the value of I2 dash? So in this case, the value of I2 dash is equal to V1 by square root of R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square. So you can see this current equation becomes very simple. So there is no need to go for any Thevenin's theorem approach to calculate VTH, RTH, XTH. There is no need to go, go for any network reduction technique. And in this case, I naught will be V1 per phase by JXM, and I1 will be I naught plus I2 dash. Like this we can calculate. And how to calculate the torque? It is 180 by, I'm writing directly, 2 pi ns V1 square by R1 plus R2 dash by S whole square X1 plus X2 dash whole square into R2 dash by S. In place of that I2 dash square, I'm writing that equation, I get the torque equation. So tomorrow, if the question is like this, what is that? See, these equivalent circuit parameters are given to you. What are those equivalent circuit parameters? These are given to you. These are given to you. And you are asked to calculate the full load torque, and at the end it is given use approximate equivalent circuit. It is given like this. Use approximate equivalent circuit. So if the data is like this, there is no need to calculate VTH, RTH, and XTH. So in all the equations which we are using, we can directly use V1, R1, and X1, right? So you can get the answer for all. So if you want to calculate full load torque, then here it is 180 by 2 pi ns V1 square by R1 plus R2 dash by SFL whole square plus X1 plus X2 dash whole square into R2 dash by SFL. So that is the difference you have to make note down. So tomorrow, if all the equivalent circuit parameters are given, and at the end, if there is a tagline given, use approximate equivalent circuit, then can I say there is no need to find out V Thevenin's, R Thevenin's, and X Thevenin's. In place of that, we can use R1, X1, and V1 in calculating all the performance parameters. Is this point clear? Confirm me. Is this point clear? Confirm me. Right? I'll write a note here. I'll write a note here. For approximate equivalent circuit, for approximate equivalent circuit, for approximate equivalent circuit, there is no need to find out, no need to find out VTH, RTH, and XTH. In place, use V1, R1, and X1 in all the above equations. Equations. Is it clear? Confirm me. Is it clear? Confirm me, all of you. Right. Done. Next one is note. So you can understand all this. First, let me finish. Note. If the no load current is neglected, no load current is neglected. If no load current is neglected, what is the value of I naught? 0. If it is 0, you can see this branch, I can show it as a open circuit. I can show it as a open circuit. Then what will be the equivalent circuit? So here I1 is equal to I2 dash is equal to V1 by square root of R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square. I hope you understood this. So even for no load, current is also neglected. There is no need to calculate VTH, RTH, XTH. In all the cases, we can use V1, R1 and X1. Here also, in place of VTH, RTH and XTH, use V1, R1 and X1. X1. I hope this is clear. Confirm me all of you. Confirm me all of you. Just only few. What about others? All should raise. Right. So this is something about your equivalent circuit analysis. Right. So here, what is the twist that may be asked in this is that also I'll explain. That question was asked twice in gate. I'll explain that. What is the twist that may be given asked means what is the equation for starting current? So in place of this, yes, I have to write 1, right? What is the equation for starting current? So starting current is equal to V1 by square root of R1 plus R2 dash square plus X1 plus X2 dash whole square, right? This is the equation for starting current. Can you agree with me? Please tell. Can you agree? Right. Now, what is that twist in this means? See, twist means here R1, R2 dash, X1, X2 dash, Xm are given for V1 voltage and F1 frequency. They are given for a V1 and F1 frequency. But if we are asked to calculate the starting current for V2 and F2, that means the voltage is different, the frequency is also different. Then first you need to find out the parameter which varies with frequency. Which parameter which varies with frequency? X1 and X2. And even Xm also varies with frequency, but that is not there in the equation, we can ignore. So can I say X1 nu is equal to X1 volt into F nu, that is F2 by F1. Similarly, X2 dash nu is equal to X2 dash volt into F2 by F1, the new frequency. Then I start new for a new voltage is V2 by square root of R1 plus R2 dash square plus X1 new plus X2 dash new whole square. This is the starting current. I hope you understood the difference. Is it clear? Confirm me all of you. Confirm me all of you. Right. So this question was asked twice in your gate, but keep one thing in the mind that always the voltage should be phase, the current should be phase. Accordingly, you can convert that into line and phase. I hope this is clear. Confirm me all of you. Raise the hands. Now, before we proceed with the next topic, let me just update to you what is that we have learned as of now. Why? Because I told you many times before we proceed, what is that we are learning? First, we should know what is that we have to learn. Then after that, we can learn that topic. See. So if anyone questions you, or as of now, till now, what is it you have learned in induction motors? Then you can see the same story. Basic starting, we have learned the basic laws. Then after that, the concept of rotating magnetic field. After that, we have learned how to design a induction motor, the preliminary or the primary steps, frame, core, like that. We have seen the types of slots, the concept of pole formation, the different type of rotors, their advantages, their disadvantages, right? Like that, we have seen everything fundamentally with respect to construction. After that, we have learned the working principle of an induction motor. Then we have learned the relative speed concepts in that. After that, we have learned what is called as the torque angle, the load angle. Then after that, we have seen how to find out the performance parameters of an induction motor without conducting any test on the motor directly by building up a equivalent circuit. First we have first we have constructed the equivalent circuit of a rotor, and from that rotor equivalent circuit we have seen how to find out the performance parameter. After that, we have constructed or built up the total equivalent circuit of an induction motor. Then we have seen how to find out the complete performance of a three-phase induction motor. So if anyone questions you, is it possible for you to tell the complete performance of an induction motor if the equivalent circuit parameters are given to you? Yes. I hope it is clear. Up to this we have learned. Please confirm me. Confirm me. Right. The next point is, whatever the induction motor you have designed, it is true that this induction motor is a self-starting motor. Why? Because the relative speed between the two fields at starting is zero. Then those stator fields and the rotor fields are stationary with respect to each other. Due to that continuous attraction and rotation, the rotor will start rotating. So it is a self-starting motor. But very unfortunate thing is, this stupid induction motor will draw high currents, deadly currents, very high currents during starting. So can you please explain what is the reason for drawing high starting currents? And if such high starting current flows in the windings, both stator and rotor during starting, the ohmic losses will be very high and the windings will get damaged. So now we are going to see what is the reason for high starting currents and how to control such high starting currents. Now we are going to talk about the starting methods. So how to control the high starting currents. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. Starting methods. Starting methods. Starting methods. I'm reminding you once again, our class will be around 8:45, 9. I'll stop. Please remember. Starting methods. So whenever you come across this term starting methods for a three-phase induction motor, please remember that it is not for starting the motor, it is to limit the high starting current. So right, the purpose of starters for a three-phase induction motor is to limit the high starting currents. High starting currents, right? Fine. Now I'm going to raise three questions and I'm going to find out the answers for those three questions. What are those three questions? Means first question, why the currents drawn during starting is only high? Why the running currents, or once the motor is in motion, once the motor is rotating, the currents will be normal and safe, right? First question is why the starting currents are high? Why starting current is high? Second, why the running current is normal? Normal means within the range, is low or normal. Then to control high starting current, what we need to do? So these are the three questions we have for us. Now let us see the answers for these three questions one by one, right? Now I'll take the equivalent circuit of the rotor. Then from that we can just answer many things. Equivalent circuit of the rotor. Circuit of rotor. So during running conditions, running conditions. So if I try to draw this equivalent circuit, it is R2 jx2 naught. This is R2 into 1 by s minus 1. This is E2 naught. This is I2. So this is the rotor equivalent circuit during running condition. Then what is the equation for this I2? I2 is equal to E2 naught by square root of, please try to answer to these questions. Square root of R2 plus R2 into 1 by s minus 1 whole square plus x2 naught whole square. So this is the equation for the rotor current. Then what is the equation for the rotor ohmic losses? I2 square into R2. The input current is I naught plus I2 dash, which is K into I2. Then input ohmic losses are I1 square into R1. So these are some equations pertaining to this rotor circuit during running conditions. Now, in general, the values of R2 and X2 naught will be very, very less. Let us consider R2 values and X2 values. If I take R2 is equal to something like 0.12 and X2 naught is equal to say 0.85, say, then the motor is operating at a slip of 0.04. Then what will be the value of R2 into 1 by S minus 1? It will be some 2.88 ohms. Now I'm trying to answer to my question, why the running currents are normal and safe. So please see, even though the rotor resistance and the standstill leakage reactance values are very, very less for a design motor, due to the presence of R2 into 1 by S minus 1, the overall rotor impedance will be very, very high. You can see this is a smaller value, this is a smaller value. But due to the presence of this resistance, load resistance, then you can see this impedance value will be very high. Due to this rotor current will be less. When rotor current is less, rotor ohmic losses will be less. As the rotor current is less, the stator current will be less. The stator ohmic losses are also less. And hence, the losses in both the windings will be less. The temperatures will be less. The insulation coating will be safe. The windings will be safe. So if anyone questions you, generally we design any winding with low resistance and low leakages. Why? Because you know that if the leakages are more, then obviously the power transfer to that circuit will be less. And if the winding resistance is more, the losses will be high. So generally we design any winding with lesser value of R2 and lesser value of X2 naught. But even though why the running currents are safe and the running currents are limited means, it is true that the rotor winding resistance is less, the leakage reactance is less, but due to the presence of the load impedance R2 into 1 by S minus 1, the overall, the total impedance of the rotor is very high. As the rotor impedance is very high, the rotor current will be less. When the rotor currents are less, and obviously the stator currents will be less. When the stator currents are less, then obviously the losses in both the windings will be less, the temperatures will be less, the windings will be safe. I think this point is clear. Confirm me, all of you. Right? Done. Is this point clear? Confirm me, all of you. Confirm me, all of you. Right. Once again, I'm repeating. What is the reason that? What is the reason that the running currents are safe? The running currents are safe means I can say even though the values of R2 and X2 knots are very less, due to the presence of the load impedance, due to the presence of this load impedance, the overall rotor impedance will be very high. As the overall rotor impedance is very high, the so-called as the rotor current will be less, the stator current will be less, the ohmic losses in both the windings will be less, the temperatures will be less, the insulation which we are coating on the windings are safe. When the insulations are safe, there is a proper insulation between the conductors, between conductor and core. The windings will be safe and the machine will be safe. Absolutely no issue we are having with the running conditions. I think this point is clear. Confirm me, all of you. Confirm me, all of you. In other way, what is the relative speed we are having between the stator field and the rotor conductor? Relative speed is ns minus nr. Relative speed will be ns minus nr. When the relative speed between the field and the rotor conductors is very, very less, the flux cuttings will be less. When the flux cuttings are less, right? When the flux cuttings are less, then the EMF induced in the rotor conductors will be less, currents will be less, ohmic losses will be less, and the temperatures will be less, and windings will be less, right? Why? Because say in this case, the speed is the rotor stator field is 1500, the rotor speed is say 1440. You can see the relative speed is less. Relative speed is less. Flux cuttings are less. Then EMF induced in the rotor conductors is less. Currents are less. Ohmic losses are less. Temperature is less. Winding is safe. Winding is safe. And hence, there is no absolute issue with the running current. Is this point clear? Confirm me, all of you. Right? Done. Is it clear? Right. One more third way I can explain this is one way of explaining. This is another way of explaining. What is the third way of explaining is the primary current I1 is equal to V minus E1 by Z1, right? And this E1 is directly proportional to the resultant flux. When the motor is running with the speeds closer to ns, then the relative speed will be less, the flux cuttings will be less, I2 will be less, the flux produced by the rotor current phi2 will be less, the opposition to the main field will be less, then this E1 will be almost closer to V, then that current will be less and hence the winding losses will be less and the temperatures will be less. Why? Because when there will be a more change in the value of E1 means when there is a change in phi r. But obviously as the rotor currents are very less, then obviously the phi2 magnitude will be less, the opposition will be less, there is no much change in the value of E1, there is no much change in the value of I1. The I1 is very, very less and obviously the winding currents will be small, the losses will be less and the temperatures will be safe. I think this point is clear. Is this point clear? Confirm me. Confirm me. Right. So tomorrow if anyone questions you, can you please tell me, what is the reason, for normal currents during running? So in cut short, I can say the relative speed between field and conductors will be very, very less. As relative speed is less, rotor currents will be less. When the rotor currents are less, stator currents will be less. When both stator and the rotor currents are less, obviously the ohmic losses will be less, the temperatures will be less, and windings will be safe. That is one way. Other way is as load impedance is present in the rotor circuit, R2 into 1 by S minus 1 is present in the rotor circuit. Due to that, the overall impedance will be more. Due to this, the rotor currents will be less, stator currents will be less, and hence the windings will be safe. Third one is back EMF is present in the rotor circuit. Motor circuit. Back EMF E1 is there in the stator winding. When E1 is there in the stator winding, then the current run from the circuit will be less. Then obviously the ohmic losses will be less and the temperatures will be less. How can you say there is a presence of E1? Means as the rotor currents are very, very less. Why? Because the speed is very closer to NS. Already this was discussed. Then the I2 will be less. The magnitude of phi2 will be less. If I'm trying to draw the phasor diagram, this was already explained. This is phi r, this is E2, and theta 2 is equal to tan inverse of S x2 naught by R2. Then you can see the slip is very, very small. Why? Because the speeds are very close. Then this I2, theta 2 will be very less. This theta 2 will be very, very less. When this theta 2 is very less, so this is I2 sine theta 2. As theta 2 is very, very less, this component will be almost to zero. The component of this rotor flux, a 180 degrees to the main field will be very, very less. The opposition to the main field will be very, very less. Then flux in the air gap will be almost maximum. E1 will be almost equal to V1. The current drawn will be less, and obviously the windings will be safe. So which fellow is present in the stator during running condition means the back EMF. That E1 will be opposing that E1, and those magnitudes will be almost the same, and hence the current drawn from the source will be almost less. I think this point is clear. Confirm me all of you. Confirm me all of you. So like this you can answer why the current drawn from the source at starting will be less. Now let me explain why the current drawn during starting will be high. Exactly opposite to this. Exactly opposite. At starting, what happened? At starting, NR is equal to 0, S is equal to 1. Then this load impedance R2 into 1 by S minus 1 will be 0. Then what is the rotor equivalent circuit? The rotor equivalent circuit is R2, X2, and this is shorted. This is shorted. This is R2, this is J, X2 now. This is E2. In place of S, I wrote 1. So this is I2 start. Well, this is the equivalent circuit at starting. What is the starting current now? I2 start is equal to E2 naught by square root of R2 plus 0 whole square plus X2 naught square. Then the rotor ohmic losses at starting into R1. Then what is the first reason? What is the first reason for high starting current? What is the first reason for high starting current means? As I told you that the leakages in the rotor circuits will be less, the resistance will be less, and hence the values of R2 and X2 naught will be very less. But very unfortunately at starting, the load impedance is absent. The load impedance is absent. As the load impedance is absent, then as the values of R2 and X2 naughts are very less, the total impedance of the rotor circuit will be very, very less. And hence these currents will be very high, 5 to 8 times of full load current. Full load current. So such high currents will be flowing in the rotor winding, and hence these rotor ohmic losses will be more, stator ohmic losses will be more. The temperatures will be very, very high. Due to these high temperatures, that insulation will melt, and when the insulation melts, obviously the windings will get damaged, right? So which fellow is not there in the motor circuit or rotor circuit at starting means the load impedance. Why the load impedance is not there in the circuit at starting means as speed is 0. When speed is 0, the slip will be 1. when slip is 1, that load impedance R2 into 1 by S minus 1 becomes 0. That fellow went to T to have a T. That fellow is not there in the rotor circuit. And hence the rotor currents will be high. The stator currents will be high. I think this point is clear. Confirm me all of you. Confirm me all of you. Right. Done. In other way, I can tell. In other way, I can tell. What is the relative speed? Relative speed is ns minus nr. At starting, nr is equal to 0. Then the relative speed is 1500. When the relative speed is 1500, flux cuttings will be maximum. EMF is maximum. Current in the rotor circuit will be maximum. Then ohmic losses will be maximum. Temperatures will be very high. Insulation melts. Windings damages. I think this point is clear. At a running condition, the relative speed is less, flux cuttings are less, EMFs will be less, currents will be less, ohmic losses will be less, windings will be saved. But during starting, the relative speed is ns, flux cuttings will be maximum, EMF will be maximum, currents in the rotor circuit will be maximum, then the ohmic losses will be maximum. I think this point is clear. Is this point clear? Or what is the question of first point once again? What is the first point? See, which fellow is not there in the rotor circuit? This load impedance is not there. The load impedance is nothing but a variable which depends upon slip. At starting, what is the value of slip? 1. When the value of slip is 1, what is the value of load impedance? It is becoming 0. When it is becoming 0, what happened to this overall rotor impedance? It will be very less. Why? During running condition, the overall impedance will be high, means due to the presence of this. This is nearly 2.88 ohms. Because of that, the overall impedance will be very high. The currents will be less. But here, which fellow is not there in the rotor circuit, means the load impedance. Because of that, the currents will be very, very high and the temperatures will be very high. Is this point clear? Anonymous attendee, now you are clear? Right, done. So, and hence the currents will be high and the windings will be anonymous attendee. Is it clear, Baba? Right, done. So like this, the things can be explained. One more and very, very important thing is the back EMF is absent in the rotor, in the stator winding. Why the back EMF is absent? You can see this is phi r, this is E2, and theta 2 is equal to tan inverse of S x2 naught by R2. And at starting, S will be approximate, starting S is equal to 1, then this current will be almost lagging this by an angle 90 degrees, almost by an angle 90 degrees. Then you can see this phi 2 will be exactly 180 degrees to phi r. Then at starting, the flux in the air gap will be almost to 0. When the flux in the air gap is almost to 0, then E1 will be almost to 0. When E1 is almost to 0, what is that stator current? V minus 0 by Z1. So such a high currents will flow in the motor winding and windings will get damaged. So which fellow is absent during starting means the back EMF is absent. Back EMF is absent and hence the winding currents will be very, 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 very high. So these are the two questions and two answers. I'll repeat once again. Please, anonymous attendee, you listen once again, Bhavan. See, what is the reason for high starting currents? Right, I'm explaining point 2 once again. High starting current. So the answer to this can be explained by 3 ways. One is with respect to that equations. So the value of R2 and X2 knots are very small, very less. We design like that. But additionally, that R2 into 1 by S minus 1, which is supposed to be in the rotor circuit, that fellow is not there in the rotor circuit. Why? Because that value literally becomes 0. As that value becomes literally 0, the rotor impedance will be very, very less. When the rotor impedance is very less, the rotor currents will be high, the stator currents will be high, the temperatures will be high, the windings will get damaged. That is one way. The second one is the relative speed between the field and the rotor conductors at starting will be ns. Then as a result, the flux cuttings will be more maximum, EMF maximum, current maximum, ohmic losses maximum, then windings will get damaged. Third way is the back EMF is not there in the stator winding. Why? Because the flux in the air gap at starting will be almost to zero. Why? Because the rotor flux is cancelling out the main flux. It is almost to zero at starting, and hence this E1 will be zero. The currents will be almost high. So because of such high current, the windings will get damaged. Is it clear? Confirm me, all of you know. Confirm me, all of you know. Then what is the reason that the running currents are safe? The running currents are safe because the relative speed is less, because the back EMF is present, because the load impedance is present. So all these fellows are going to control the the running currents, right? So these are the two questions and two answers, right? Next one is how to control such high currents. Why? Because if such high currents are flowing in the windings will get a damage. How to control such high currents? So if you look into the starting current, if you look into the starting current, it is given by E2 naught by square root of R2 plus or R1 plus. So R2 plus 0 whole square plus X1 plus, sorry, I'm writing that equivalent circuit analysis. X2 naught whole square. This is the equation for your starting current. By looking into this equation, one can say that if you are controlling the secondary current, rotor current, then the primary current will be controlled. So what are the three ways we are having to control this current is, one is this E2 naught, the other one is this resistance part, third one is this leakage reactance part. Now if I'm talking about a slip ring induction motor, so in slip ring induction motor, we have the provision of adding resistance. By adding resistance, we are increasing the rotor resistance. When we are increasing the rotor resistance, the overall rotor impedance will be increased. When the overall rotor impedance is increased, the rotor current will be less, the starting currents will be less, and hence we can control and hence we can limit the high starting currents. So if anyone questions you, Arababa, can you please tell me how to control such high starting currents? Means I can tell. In case of slip ring, as we are already adding some resistance to improve the starting torque, that added resistance will control the starting currents also. So in case of slip ring induction motor, if you are adding some additional resistance in the rotor circuit, the starting currents will not be high. The starting currents will be obviously in controlled manner. So there is no need to worry in case of slip ring induction motor. But whereas in case of squirrel cage induction motors, we don't have the provision of touching this rotor circuit. Why? Because the rotor circuit is permanently shorted. So we don't have the provision of touching, disturbing the rotor circuit. So how to control such high starting current means by varying only this parameter E2 naught. So this E2 naught I can approximate it as E1 by A, and this one is nothing but V1 by A. So finally the starting current depends upon your supply voltage. So in case of squirrel cage induction motor, if you want to control such high starting current, the only method we are having is to start the motor with reduced voltage, right? To start the motor with reduced voltage. So one question, sir, in case of squirrel cage, if bars are made of aluminum, then resistance will be high. No, sir. See how much high, that high resistance cannot be like made to control such high starting currents. Please remember, the value will be very, very high. Please remember. So what is that? What is A? Are Baba, Amit Varma, Vikram Pujari. A is the turns ratio. See, already you have solved the numericals also. A is the turns ratio, right? Please. So the only one method we are having to control such high starting currents in case of a cage rotor is to start the motor with reduced voltages. So this is the only method we are having in case of a cage rotor to control such high starting currents. So these are the three questions and three answers. Let me mix up once again. Let me once again conclude. If anyone questions you, why the starting current drawn by a three-phase induction motor, right, is very high? The answer is the relative speed between the stator field and the rotor conductors is very high, ns minus 0. Flux cuttings will be high. EMFs in the rotor conductors will be high, currents will be high, the stator currents will be high, ohmic losses will be high, the temperatures will be high, and windings will get damaged. In other way, the load impedance R2 into 1 by S minus 1 will be absent. Why? Because that S is 1, that fellow is absent, the rotor impedance will be less. The overall impedance will be less, the current drawn by the rotor and the stator will be high, ohmic losses will be high, temperatures will be high, and windings will be damaged. Or the back EMF is absent in the stator winding, which will draw very high currents, right? Because of this, the motor will draw very high currents. Is this point clear? Confirm me, all of you. Why the running currents are safe? It is exactly opposite to this. The load impedance is present in the rotor circuit, which makes the rotor impedance high, the rotor currents less. The back EMF is present in the circuit, which will make the current drawn from the source will be reduced. The relative speed is less, and hence the currents will be less. Third point is how to control such high starting currents. So in case of slip ring induction motor, whatever the resistance we are adding, that will control the high starting currents. But whereas in case of squirrel cage induction motor, we don't have the provision of adding any resistance in the rotor circuit. The only way, the only one method to control such high starting currents in case of a cage rotor is to start the motor with reduced voltage, right? So these are the three questions and three answers, right? Please confirm me if you have followed this. Raise the hands. All right. Now the question comes. It is true that we are controlling the current by reducing the voltage, but you know that starting torque is directly proportional to V square. So when you are starting the motor with reduced voltages, then obviously the starting torque will be reduced to too much. 10% decrease in voltage will decrease 20% of torque. So we need to sacrifice the starting torque. So does it affect the performance? Generally, no. The reason is we use this squirrel cage induction motors for raising loads. What is the meaning of raising loads? Means if I try to draw the torque slip characteristics, so they are like this. So this is with rated voltage. Say the load characteristics, load is driving a fan. Let me consider this is a fan load, right? Directly proportional to n square. So the starting torque will be almost 0 for the load. So if I'm trying to reduce the voltage, then the characteristics will be like this. Like this. So that means the starting torque will be reduced. You can see the starting torque is reduced. But this torque is enough to drive the load. So this torque is enough to drive the load. So even though the voltage is reduced to reduce the starting current, the starting torque will reduces, but this is not going to affect the performance much. Why? Because we use these induction motors for raising loads. For raising loads, what is the torque required at starting? It is very, very less. But the thing is, once the motor starts rotating, then you are not supposed to keep that voltage low. You have to increase the voltage slowly. Why? Because once the motor starts rotating, the relative speed will start decreasing, the rotor currents will start decreasing. Then you have to increase the voltage proportionately. So you are not supposed to keep the voltage low. So during starting, you're starting with low voltages, but once the motor starts rotating, you have to increase the voltage proportionately. Finally, you need to operate the motor always with rated voltage, not less than rated voltage. Is this point clear? Confirm me. Right. So one of the question raised by anonymous attendee, sir, high current occurs in stator, right? It is not in the question, it is not in the stator, even it is in the rotor also. So only basing on the rotor current, the current drawn from the stator will be decided. If the rotor rotates with the speed closer to ns, rotor current I2 will be less, the stator current I1 into K into I2 will be less. Please remember. So these are not like separated. Why? Because the current for the stator and the rotor will be drawn from the source, only single excited machine. It is not like stator current is high, rotor current is not high. So the current drawn from the supply will be decided by the rotor current only. Anonymous attendee, please remember that. Right? Please. Sir, is K is equal to A? So please refer K is not equal to A. K is equal to 1 by A. Please. Right? So he's having wonderful doubts. Amit Vikram Pujar. So K cannot be A, Baba. So it is a fundamental thing. Already I told you, K is equal to 1 by A. So K is defined as N2 by N1. but A is defined as N1 by N2. If I'm correct, please refer that. Fine. So one thing, so how to control such high starting currents means starting the motor with very low voltages. But when you are starting the motor with low voltages, the starting torque will reduce. Does it affect the performance? No. Why? Because we are using this induction motors for raising load characteristic. Even though the starting torque is reduced little bit, that is not going to affect the machine. The machine will start rotating. But once the motor starts rotating, then obviously the voltage has to be increased. I think this point is clear. Confirm, all of you? Right, done. So, sir, can you please explain how I1 is equal to KI2? See, if you look into this phase, that equivalent circuit, I1 is equal to I0 plus I2 dash. So, I0 plus I2 dash is K into I2. If I neglect this I0, then I1 is approximately equal to K times of I2. Please remember that. Please remember that. So, by reducing both V at starting, I think so disadvantage are, I didn't get you. Right? See, remember we are not keeping this voltage low for long time. It is only for starting. Once the motor starts rotating, then we try to increase that. What happens if voltage is not increased? What if voltage is not increased? We can see if voltage is not increased. Very good question. So if you are not increasing the voltage, you are keeping the voltage here only. See like this. Then what happens? This maximum torque value will decrease. Instead of operating the motor here closer to NS, the motor will operate here with the speeds away from NS. The temperatures will be the relative speed will be high, currents will be high, temperatures will be high. The efficiency of the motor will be very less. Then overall performance of the motor will be very poor. So for that reason, we need to always operate the motor with always equal to rated voltage. Already I told you, right? Please confirm me this. All of you confirm me this. Right. So this is something about your so-called as starting methods or starting. So once again, revise this. After that, we can proceed. See, revise. So if anyone questions you, why we need a starter? Then I say, the purpose of starters for a three-phase induction motor, as the name says, is not for starting motor, but it is only to limit the high starting current. Sir, we don't apply rated voltage. That's what I told. So it is only to limit the high starting currents. Now the question comes, why the starting currents are very high? We have seen the reason. Why the running currents are safe? We have seen the reason. Then in case of slip ring, how to control such high starting currents? By adding some resistance. But whereas in case of squirrel cage induction motor, as we don't have the provision of adding high resistance in the rotor circuit, the only method is to start the motor with reduced voltage. So we start the motor with reduced voltage. Then once the motor picks up the speed, then we increase the voltage, and finally the motor has to be operated with rated voltage, right? Please remember this. But what is the main problem we are having with a starting the motor with reduced voltage means the starting torque will decrease. But this is not going to affect the motor much because we use this induction motor, squirrel gauge induction motor for raising loads. Even though the starting torque is reduced, this is not going to affect the motor performance much. But if we keep that voltage low, right, for running condition also, then the performance will be damaged. So that's the reason once the motor starts picking up, then you have to apply the rated voltage. I think this point is clear. Confirm me. Right. Now I'll try to bring out some relationships which are very important. What are those relations? We have electromagnetic torque is equal to 180 by 2 pi ns. I call it as K I2 square into R2 by S, right? Then at starting, S is equal to 1. So this K is not N2 by N1. So it is 180 by 2 pi Ns. I call I2 is equal to I start, and electromagnetic torque is equal to T start. Then from this, T start is equal to K into I start square into R2 by 1. This is one equation. Similarly, at full load, S is equal to SFL, that I2 is equal to IFL, then TEM is equal to TFL. Then what is the equation for full load torque? It is K into IFL square into R2 by SFL. This is equation 1. This is equation 2. I'll find out the ratios of this. T start by TFL is equal to IST by IFL whole square into SFL. This is one equation which is required for all the starting methods. This is one equation. The next one is the equivalent circuit I'll take. What is that if I neglect the no load current? So this is R1, this is R1, this is JX1, this is R2 by S, this is JX2 dash. So if I'm neglecting the no load current, so this I can write it as R2 dash, that's R2 dash into 1 by S minus 1. I'll mix up these two. I call it as R01. I'll mix up these two. I call it as X01. So this circuit I can modify like this. This is the equivalent circuit of a induction motor, neglecting your no load current. Right. See, why it is C? Generally, R1 is accountable for stator ohmic losses, R2 dash is accountable for rotor ohmic losses. Instead of showing those ohmic losses separately, I'll mix up and I'll show like a only one branch, R01. That R01 is accountable for the losses in the machine. Similarly, X01 is the total leakages in the machine. Then, if I'm applying a rated voltage here, then at starting, what is the value of S? At starting, what is the value of S? At starting, S is equal to 1. Then R2 dash into 1 by S minus 1 will be 0. Then what will be the circuit here? This is R01, JX01. This is V1 per phase. This current I call it as ISC. So what is the value of ISC? Means it is the per phase voltage by R01, let's say X01. So this is V1 per phase by Z01. So this current will be how much? Means 5 to 8 times the full load current. I'll explain what is that, don't worry. 5 to 8 times the full load current. So I'm using this terminology ISC. What is that ISC means? It is the current that flows in the motor windings at starting when you are applying a direct rated voltage of V per phase. So what will be the magnitude of this current? Means it is 5 to 8 times the full load current. And if such currents are flowing in the motor winding, obviously what happened to the windings? Damages. Why I'm using this terminology short circuit means the load impedance is not present. So that is the reason I'm using it as a short circuit current. So please, I'm writing these notes, please. Don't worry, I'll repeat once again. ISC, it is the current that would flow in the motor windings at starting. It is approximately 5 to 8 times the full load current. If such high currents current flows in the motor windings the ohmic losses will be high, temperature will be high, windings will damage. Windings will damage. To limit such high currents, starters are required. I think this point is clear. Confirm me, all of you. Confirm me, all of you. Right. So, why starters? How to control currents? We have seen. Right. So I'll stop for today. So the types of starters we'll see in the next class. That is tomorrow's class. Right. But class is not over. So very important stage, the doubt discussion. I'll come back. Just let me bring the earphones. Right. See, already I told you. One question is, sir, is there any specific percentage of voltage reduced in the given 40 to 60? No. It depends upon the type of starter. We'll see that in the coming days. Don't worry. Vikrant. One question, Virukonda Satish. Sir, my doubt is how the speed of the rotor field with respect to stator is ns. Why can't be the speed of the stator field minus? See, if you want to calculate the speed of the rotor field with respect to stator, first you find out the speed of the rotor field with respect to rotor, then the speed of the rotor with respect to stator. You add these two, you'll get the answer. Sir, in case of squirrel cage induction motor, how we control the starting voltage? That we'll see in the tomorrow's class. Don't worry. Sir, this session includes single phase induction motors also. Yes. Single phase induction motors will be discussed later. Absolutely. Right? Done. Now let us see for the question and answers from the participants. Right. Bhavya. Bhavya. Hello? Hello? So maybe. Sunil. 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 Maybe technical issue. Imtiaz Pasha.
Good evening, sir.
Good evening. Yes, please.
Sir, the shunt parameter is there, no, sir? RC and XM.
Yes, RC and XM, correct?
In transformer, we can neglect, no, sir, the shunt parameter. Can we neglect in induction motor?
No. See, I told you that RC can be not neglected while you are finding out the performance using that equivalent circuit. That branch RC can be eliminated in the analysis. But when you are not considering that RC, the core losses you are not counting. So that is the reason that core losses has to be given separately. If the core losses are given separately, then you can eliminate that RC there. Understood? It is not something like you are not ignoring. You are not ignoring that. So as the core losses are given separately, so in the analysis you are not considering that branch RC. Imtiaz Basha.
Okay. Sir, one more. For finding out the equivalent circuit, we can refer to the stator, no, sir.
See, it is not for finding, Baba. It is while we are
Yes, yes,
while we are drawing the equivalent circuit, we can refer the parameters from stator to rotor. You mean to say?
rotor to stator.
So we have done the same thing. Rotor to stator we have done. What is your doubt?
Can we? Okay, I have doubt means. Can we refer the stator circuit to the rotor circuit for the finding of the I2?
Obviously, yeah, you can do it. What is there? When this side is possible, that side is also possible. Understood? You can do it. No issue. But the procedure will be complicated. You can do it. No issue. See, whatever it may be, your answer should be same. So when you are referring, then it should be R1 dash, X1 dash, R1 dash is equal to R1 into K square. Like that you have to do. Understood?
Okay, sir.
Then?
Yes, sir. Thank you, sir.
Kumar.
Hello, sir.
Yeah.
Sir, here RC is the stator copper loss related to that term.
RC is not the stator copper losses, Baba. RC is the core loss. Baba, core losses, correct.
Sir, actually, here in that equation, we taken that mechanical, electrical equivalent mechanical power minus mechanical losses plus like that.
See, if the thing is in the equivalent circuit, if the value of RC is not given, that means you are finding out the performance of an induction motor without considering the core losses. But
yes, sir.
That core losses has to be given separately.
Sir, what my doubt is that that core losses is when we go to to find the mechanical equivalent power, we use air gap power, like rotor input power, right?
No, it is not the question of air gap power. When you are calculating the net power, you are taking the gross mechanical power. From that, you are subtracting that losses.
Sir, అంటే మనకి ఇప్పుడు ఆల్రెడీ ఎలక్ట్రికల్ మెకానికల్ ఈక్వలెంట్ పవర్ ఉందంటే అది ఆల్మోస్ట్ అన్ని లాసెస్ గా అంటే స్టార్టర్ లో లాసెస్ సబ్ట్రాక్ట్ చేసిన తర్వాత వచ్చిన పవర్ కదా సార్.
ఎలా వచ్చిద్దమ్మా ఇప్పుడు చెప్పు
సార్, హౌ వి ఫైండ్ ఇన్ ద పవర్ ఫ్లో స్టేజెస్ లో మనం ఎలక్ట్రికల్ మెకానికల్ పవర్ ఎలా సార్ ఫైండ్ చేస్తాం?
సరే, ఇప్పుడు if you are not considering RC, then whatever that active power drawn from the source, will it be same or it is different?
Sir,
if you are not considering RC, let me say you are not considering RC, what will be the active power drawn from the source? Will it be same or it will be different?
Different, I think.
Different. How come? If RC is there, then there will be some component of power which is required for that RC, where you are neglecting that. When you are neglecting that, the amount of power drawn will be less.
Yes.
Understood? That means when you are
సార్, నాకు అది అర్థమైంది సార్, కానీ నా డౌట్ ఏంటంటే మనం అక్కడ ఈక్వేషన్ లో మీరు పీ నట్ ఈజ్ ఈక్వల్ టు 3 అది దట్ పీ మెకానికల్ ఈక్వలెంట్ మైనస్ పీ లాసెస్ ప్లస్ దిస్ వన్ ఆర్సీ లాసెస్, స్టార్టర్ కాపర్ లాసెస్.
ఎప్పుడు when you are not considering RC.
ఓకే, when you కన్సిడర్ చేస్తే ఆ లాసెస్ కూడా తీసుకుంటున్నాం కదా.
When your RC is there in the equivalent circuit, so that losses are already considered.
సార్ నా డౌట్ ఏంటంటే అక్కడ ఆల్రెడీ మనం ఆ సబ్ట్రాక్షన్ అనేది మెకానికల్ ఈక్వలెంట్ పవర్ నుంచి చేస్తున్నాం కదా సార్.
మెకానికల్ ఈక్వలెంట్ పవర్ ఏంటమ్మా ఇప్పుడు
సార్ 3I2² into R2 by into of 1 minus -1.
What is that power? It is the gross mechanical power developed, right?
Sir, gross mechanical power developed.
So, let me finish.
Yes, sir.
If you consider this circuit, so the stator is drawing some power is wasted in the stator losses, some power is wasted in the core losses, some power is going to the rotor, some power is wasted in the rotor copper losses, some power, the remaining power is converted into mechanical power, right? From that, if you subtract the mechanical losses, you'll get the net power. Up to here it is okay?
Okay, sir.
Now if you are not considering RC, when you are not considering RC, so whatever the power that is required for this RC is not drawing from the source.
Yes, sir.
So that has to be considered separately. So the additional power you are taking in the mechanical losses.
So that power is not considered in terms of core losses.
Yes. So that is included in the mechanical losses. Why? Because mechanical losses is a constant loss, a variable loss.
Constant losses almost.
Core losses are also
constant losses.
That's what. Understood?
Yes, sir. I understand.
Right. Any more doubts?
No, sir. Thank you.
Right. No one is raising the hands. Vishnu, Ajit.
Sir, this on regarding this starting condition only, sir.
Yeah, so, you can ask.
Sir, so generally whenever we are running an induction motor, so like you connect it to an auto transformer and variably like you'll move the dial such that you slowly increase to rated, sir.
See, as of now, I didn't explain about auto transformer. Okay. So if you are having any doubt from today's, you ask, then I'll tell you the role of auto transformer tomorrow. So the role.
I'm asking in terms of varying, sir. Just I said auto transformer just for this, citing that example.
One of the starting method is using an auto transformer, right? So using the auto transformer, we start the motor with reduced voltage. Once the motor starts rotating, then we increase the voltage to rated, using that the same auto transformer. So one of the starter you are using is a auto transformer. Is it clear, Ajit?
Yes, sir. And sir, one more, sir. To increase the resistance of this during starting, like this bars, whatever use are solid bars, no, sir, in rotor. In the case of a squirrel cage.
Yes.
If you make it hollow, then what is the issue, sir? Only mechanical aspects are the issue, or
mechanical? Then if you are making hollow, what about the effective resistance? What will be the effective resistance?
Like what I thought was that due to that skin effect, this area will reduce.
Yeah, skin effect will be reduced. But if you take a hollow conductor, what will be the effective resistance of that conductor? Current will be flowing. Now, what will be the effective resistance?
Will be more.
More. Ohmic losses. That means the current is supposed to flow uniformly throughout the conductor. But you are forcing the current to flow only in the thinner sections. In a hollow means thinner surroundings. Then that area, that surroundings will get heated up.
Okay, sir. So I mean, again, it's useless.
Same again, the problems will be increased.
Okay, sir. All
right.
Sir, that notes can we get today, sir?
Yeah. You just text me your number. Why? Because daily I used to send to the students. Please.
Okay, sir.
Right.
Thank you.
Right. Thupati Bhavani. Yes. Yes, Bhavani. Bhavani.
Sir, మీరు
Your voice is not audible, ma. Your voice is not clear. Hello. Hello.
hello.
She got disconnected. Right. So one more question, Salman Khan. Sir, if I am correct, XM is also considered to represent core component. Yes, it is a magnetizing component. See, even if you remove, there is no issue. That's the reason when we are not considering the no load current, so there is no much issue in the performance. You can see that, Salman Khan. That is what I told, right? Two party Bhavani.
హలో సార్.
Yeah, please ask.
సార్ టీ మ్యాక్స్ కనుక్కోవడానికి మీరు ఇంకో మెథడ్ చెప్పారు కదా సార్.
Yes.
లైక్ ఎస్ఎంటీ కనుక్కొని దాన్ని I2 డాష్ ఈక్వేషన్ లో సబ్స్టిట్యూట్ చేసి.
Yes, ma.
సార్ అలా కాకుండా R2 డాష్ బై ఎస్ ని డైరెక్ట్లీ ఇప్పుడు పవర్ ట్రాన్స్ఫర్ ఈక్వేషన్ లో రూట్ ఆఫ్ RT థెవెనిన్స్ రెసిస్టెన్స్ స్క్వేర్ అని రాశారు కదా సార్.
Yes.
అది డైరెక్ట్ టీమాక్స్ టీఎం ఈక్వేషన్ లో సబ్స్టిట్యూట్ చేస్తే అయిపోతుంది సార్.
ఏది చేసిన ఆన్సర్ అదే రావాలి. So if you are calculating R2 dash by S is equal to square root of R Thevenin square plus X Thevenin plus
Yes.
X2 whole dash. If you do that, if you substitute in torque equation, you will get the same thing. That is what I have done. Understood?
అదే
Yeah, you can do it. You can do it, man. No problem. Understood?
yes sir.
Right.
That's it sir.
Right,
Thank
ma'am.
you sir.
Right, ma'am. No one is raising the hands. Yeah. Ashish Raj.
Hello, sir.
Ha, Baba. Ashish
Good evening,
Raj.
sir.
Good evening.
Sir, I want to know about, sir, this phasor diagram of induction motor. Sir, I'm not understanding 5R, 5-1, 5-2. The
See,
relation.
yeah. What is the main field? What is the final field that is rotating in the air gap?
5 years.
5R, which is rotating with a speed of?
NS.
Then this flux cuts which conductors? Stator.
Sir, rotor.
Stator as
Okay,
well
sir,
as
stator. Yes.
then that EMF will lag that flux by an angle 90 degrees.
Then,
That will lag by an angle 90 degrees, right?
okay, sir.
Hello?
Okay, sir. Yes, sir. Yes, sir. Yes, sir.
Right. Now say the rotor circuit is closed. Then that current lags by an angle theta2 with respect to E2, right?
With respect to E2, theta 2. Yes, sir.
Right. So because of that I2, there is one flux phi2.
Okay, sir.
Right. Then your phi r is equal to phi1 plus phi2 phasor sum, right? If you want to calculate phi1 from phi r, what is that you need to subtract?
Sir, 5-1, sir.
Phi2. You need to subtract phi2, right?
Okay, sir. Okay, sir.
Then you just draw, if phi2 is downwards, minus phi2 will be upwards. Then you apply parallelogram of vectors, you'll get phi1.
Okay, sir. And that also, sir, about that I2 dash. That I2 dash means that transfer that side.
Yeah. What do you want?
That phasor diagram. Sir, that phasor diagram. Sir.
What is that I2 dash? I didn't draw any phasor diagram for I2 dash.
Okay, sir. Then somewhere I saw it. That's why I was asking some book or something.
See, in phasor diagram, that is something like in your transforming, your teacher might have told you that, right? That is not required here. Still, if you want, I'll explain that. Right? That is not required, but still, if you want, I'll explain. Right.
Okay, sir.
Shall I? You want me to explain?
Sir, if not required, then it's okay, sir.
No.
Sir, in work.
Yeah.
If you will, then it will be good, sir.
If you want me to explain now.
Yes.
Yeah. See, this is your V1. Then your induction motor will draw two currents. One is the loss component to supply the core losses. The other one is the magnetizing current to produce the flux. Correct?
Yes, sir.
The resultant of these two is nothing but your no load current I naught.
I know.
So because of this magnetizing current, there is one flux phi r. Yes.
Okay, sir. Yes, yes, sir. Yes.
Now that phi r, when it cuts stator conductors and rotor conductors, what is induced? EMFs.
Yes, sir.
As the rotor circuit is closed, what circuit? Current. Right? So because of this current, there is one flux phi 2. Right? So to compensate that flux phi 2, there is one more current I2 dash, which is been drawn. This will produce phi 2 dash. Then the resultant of these two currents, I naught and this I2 dash is I1. This is your theta 1. Understood now?
Yes, a load angle, sir, this theta 2.
So load angle is 90 plus theta 2. This one. This one. Load angle is always from resultant field axis and the rotor field axis. So this is your theta 1 is input power factor angle.
Okay, sir.
Understood?
Okay, sir. Thank you. Yes. Right. Sir, in workbook, sir, page number 281, sir, there is some relationship between T means torque of electromagnet and sir load torque. There are 4 figures.
So that was already I explained, right? What is that? So I have taken this induction motor characteristics and load characteristics. How to find out the stable points I told. So the same logic you apply, you'll get the answer there. Right?
Inverse, na, sir? Yes, sir, that's inverse.
Inverse. Then you have to check which point is having inverse relation, then you'll get the stable point. Understood?
And sir, about tests, sir, means induction motor tests.
SC and OC tests. No load and block.
Yes, sir. Is it in syllabus or not?
It is there in syllabus. I'll explain that. It is only just some half an hour or 1 hour. Fundamentals. Right?
Okay. Okay. Thank you, sir.
Right. Abdul Rahman. Hello. Abdul Rahman. Hello.
Hello.
Yeah, Baba. Please ask your question.
सर मैं एक स्टेटमेंट बोलूंगा सर कि अगर ये सिमिलर टू इंडक्शन मोटर की है कि नहीं कि बोलो सर. फॉर एग्जांपल मैं ट्रांसफार्मर को मैं इनपुट वोल्टेज स्क्वायर या ट्रायंगल या पल्स दिया सर इनपुट वोल्टेज, देन आउटपुट विल बी 180 डिग्रीज नेगेटिव फीडबैक फेज शिफ्ट रहता 180 डिग्रीज. द सेम वोल्टेज विल बी डेवलप इन आउटपुट साइड बट इट शुड बी नेगेटिव फीडबैक 180 डिग्रीज, राइट सर?
180 degree phase shift.
ये transformer is similar to induction motor, right, sir?
Yes, same thing is happen even in case of induction also. So your induction machine can also be access phase shifted.
तो इसका मतलब क्या है कि हम कौन सा भी स्क्वायर हो, ट्रायंगल हो, इंडक्शन मोटर को हम सप्लाई दिए तो
we have phase shift just like your transformer. Why? Because that secondary voltage E2 will have a phase shift of how much degrees? 180 degrees.
When compared to V1, right, sir?
हाँ.
अच्छा. ठीक है.
Okay.
सर और एक सर आखिरी का नॉर्मल का.
Yeah, please ask.
मैं आपका फॉर एग्जाम्पल कौन सा भी एक फैकल्टी का जो क्लास सुनते से टाइम पे पैरेलल नहीं हो रहा सर. पैरेलल का तो while ongoing the class it should be not to ये नॉर्मल मेरा ये सब प्रॉब्लम है. इसका थोड़ा सॉल्यूशन बता दो. क्या है तो क्लास सुनते से टाइम पे नोट्स नहीं हो रहा कंटिन्यूएशन.
See one thing, Baba. See, I agree with you. Why? Because like sometimes it may be difficult for you to write the notes and attend the class. Not only you, many of the students will have an issue. The thing is, I think you are having 2 to 3 times you can rewatch the same video, right?
हाँ सर, यही हो रहा है सर। फॉर एग्जांपल देखे तो नोट्स लिखने के लिए 3 to 4 hours पकड़ रहा सर।
Yeah,
अगर
why?
मैं
Because
नोट्स जी
if you write the notes, that will be a added advantage to you. See, I told you already when you called me. See, it all depends upon your hard work. See, if you're not able to write the notes at the same time, you have to work additionally for 2 to 3 hours. You have to rewatch the video, then slow down the speech, then take down the notes and complete your preparation. Why? Because we have certain constraints. It cannot be like I can wait till all the students can write. Why? Because it is difficult from my side to do that. So you are having the provision to listen that video 3 times. Then one time you listen and try to write your notes one. Then you can find the notes. Understood, Rahman sir?
हाँ ठीक है, थैंक यू सर।
Right.
हेलो।
Yeah. Right. Next. Right. So no one is raising the hands. So yeah, someone, Vaishnavi. Yeah, please.
హలో సార్.
Hama, please, Vaishnavi.
సార్ మీరు క్లాస్ స్టార్టింగ్ లో ఒక పాయింట్ చెప్పారు కదా సార్, టు రెడ్యూస్ కాంప్లెక్సిటీ ఆర్సీ ఇస్ నాట్ కన్సిడర్డ్ ఇన్ ద అనాలిసిస్, బట్ హౌఎవర్ వైల్ క్యాలిక్యులేటింగ్ నెట్ పవర్ ఇన్ అడిషన్ టు మెకానికల్ losses should be subtracted from gross mechanical power analysis.
Yeah, in addition, ఇప్పుడు see, if you consider the complete equivalent circuit, in that complete equivalent circuit, that RC is there, right?
Yes sir.
So when that RC is there, whatever the gross mechanical power you have calculated, right, it will be after that stator core losses, right? What do you mean by that? Say the motor is drawing some power. Out of that power, stator copper losses are subtracted, stator core losses are subtracted, then the power is coming to the rotor.
Yes sir.
Then after that power, a part of the copper loss in the rotor is subtracted, then you are getting the gross power.
Yes sir.
And from that, mechanical losses has to be subtracted to get the net power. This is the flow, correct?
Yes sir.
But unfortunately, if you are not considering that RC, that means which losses you have not considered there?
Copper losses.
That means whatever the power the machine is drawing, whatever the power that is machine drawing, so only stator copper losses are subtracted, but the stator core losses are not subtracted. So whatever the power that is coming to the rotor, it is only after neglecting stator copper losses. Stator copper core losses are not considered there. Understood? Then from that rotor power, you are subtracting the rotor losses. Then you are getting gross power. And from that gross power, mechanical losses plus these copper core losses has to be subtracted in that. Then you will get the net power. Is it clear?
Yes sir.
అర్థమైందా?
అర్థమైంది సార్. ఇంకొక డౌట్ సార్, మామూలుగా ఇప్పుడు ట్రాన్స్ఫార్మర్ లో నో లోడ్ కరెంట్ చాలా తక్కువ ఉంటది, తక్కువ డ్రా చేస్తుంది, కానీ ఇండక్షన్ మోటార్ లో నో లోడ్ కరెంట్ అనేది ఎక్కువ ఉంటది అని చెప్తారు కదా సార్?
నేను చెప్పలేదే, no load current is always less. Why? Because the speed will be very closer to ns. See, no load in the sense the rotor is not stationary. No load means the speed is closer to ns. Standstill means rotor is stationary. Starting current is very high. Whatever I told is the starting current, but not the no load current. No load current means when the rotor speed is closer to ns. When the rotor speed is closer to ns, the rotor circuit will be open more or less. ఎందుకంటే లోడ్ ఇంపెడెన్స్ ఎలా ఉంటుందమ్మా, R2 into 1 by s minus 1, as is s is approximately equal to 0, that load impedance will be approximately infinity. అంతే, కరెంట్ చాలా తక్కువ ఉంటుంది అక్కడ. అర్థమైందమ్మా? రైట్.
థ్యాంక్ యూ.
రైట్. Right. No one is using the. I'll stop for today.